Does the universe remember everything? Have you ever had a thought so fleeting you were sure it vanished forever? Or witnessed a momentary event, convinced it was lost to time? What if you were wrong? What if the universe has a perfect memory? From the explosion of a distant star to the quietest whisper in a forgotten room. Every single event may be permanently etched into the very fabric of reality. We're going to explore the extraordinary idea that the universe is a cosmic archive, where nothing is ever truly lost. The great cosmic contradiction. Our story begins not with memory, but with the ultimate loss. It starts with one of the most terrifying and mysterious objects in the cosmos, a black hole. For decades, we saw them as cosmic dead ends, a place where gravity is so intense that nothing, not even light, can escape. They're the universe's ultimate trash cans. Anything that crosses their boundary, the event horizon, is seemingly gone for good, crushed into an infinitely dense point we call a singularity. In old-school classical physics, this isn't a huge problem. You throw something away, it's gone. But here's the issue. Our modern understanding of the universe rests on two giant pillars: Einstein's general relativity, which describes gravity, and quantum mechanics, which governs the bizarre world of the very small. And according to a sacred rule of quantum mechanics, something vital can never, ever be destroyed: information. Now, what is information to a physicist? It's not just words in a book or data on your phone. It's the unique, specific state of every particle in a system. Think about a single atom. Its information is its location, its velocity, its spin, its entire identity. Now, think of a cup of coffee. The information of that coffee is the sum total of the properties of every particle that makes it up. A core principle of quantum physics says this information must always be conserved. You can burn the book, but the information about the ink and paper is just transformed into the information of the resulting smoke and ash. You can smash the phone, but the quantum state of its parts is just rearranged. The information gets scrambled, but it's never deleted. If you had a supercomputer powerful enough, you could theoretically reverse the process and reconstruct the original object. Information, in this sense, is permanent. This is where the conflict explodes. In 1974, the brilliant physicist Stephen Hawking made a discovery that shook physics to its core. He found that due to weird quantum effects at the edge of a black hole, they aren't completely black. They slowly leak radiation, a faint glow we now call Hawking radiation. Over immense timescales, trillions upon trillions of years, this energy leak causes the black hole to lose mass and, eventually, evaporate completely, vanishing in a final puff of radiation. And here's the paradox, a contradiction so profound it threatened to break science. What happens to the information of everything that fell into the black hole? The coffee, the star, the encyclopedia? According to Hawking's initial calculations, the radiation that escapes is random. It contains no information about what the black hole ate. It only knows the black hole's mass, charge, and spin. This is the no-hair theorem, the idea that black holes are remarkably simple, bald objects. When the black hole is gone, the information seems to be gone too, utterly erased from the universe. This is the black hole information paradox. It gave us a terrifying choice: either that sacred law of quantum mechanics is wrong, or our understanding of gravity is incomplete. For physicists, this was a declaration of war between the two pillars of modern science. If information can be lost, then the universe is fundamentally unpredictable. The past could be erased, and the link between cause and effect could be broken. The very logic of reality as we know it would crumble. This puzzle forced scientists to ask a new question: if information can't be destroyed, where does it go? The quest to solve this paradox of cosmic loss accidentally kicked off the search for the universe's memory. The scars of spacetime. To understand how the universe might remember, we have to look at the fabric of reality itself, spacetime. According to Einstein, Space and time aren't a static backdrop, they're a dynamic, interwoven fabric. Massive objects warp this fabric, and that's what we feel as gravity. When those objects accelerate, they create ripples in spacetime gravitational waves. For a century, these waves were just a theory. But in 2015, the LIGO Observatory made history by detecting faint ripples from two black holes colliding over 1 billion light-years away. It was a monumental achievement, opening a new way to listen to the cosmos. But these waves might hold a deeper secret. There's a predicted phenomenon called the gravitational memory effect. Imagine dropping a stone into a still pond. Ripples spread out, but afterward, the water is flat again. Gravitational waves were first thought to be similar. They stretch and squeeze spacetime as they pass, but then it should return to normal. The memory effect says that's not quite right. When a catastrophic event happens, like two black holes merging, the burst of gravitational waves doesn't just pass through spacetime. It leaves a permanent kick, or scar, on the fabric of reality. After the wave has passed, the distance between 2 points in space will be permanently, though minutely, altered. Spacetime literally remembers that the wave passed by. This isn't just a fringe idea, it's a direct prediction of Einstein's general relativity. While the effect is too small to have been measured directly yet, future observatories like LISA are being designed with the sensitivity to spot it. Think about what this means. Every violent event in cosmic history, every supernova, every black hole collision has left a permanent, indelible mark on the geometry of the universe. Space-time isn't a blank slate. It's a vast historical document written in the language of gravity. The ripples fade, but the imprint remains. The universe, in a very real, physical sense, bears the scars of its own past. This is our first major clue. The universe has a physical mechanism for recording events. But a scar is one thing. How does this help with the specific information of a cup of coffee? For that, we have to look at a strange discovery about what might be growing on the black hole's surface. The soft hair of black holes. The information paradox was born from the no-hair theorem. The idea that black holes are simple and bald, defined only by mass, charge, and spin. Any other information is lost. A black hole made from a star is identical to one of the same mass made from encyclopedias. But in recent years, a new idea has taken hold, developed by physicists like Stephen Hawking in his final years. They found something everyone had missed. They realized black holes might not be bald after all. They might have a halo of soft hair. This isn't literal hair, of course. It's a metaphor for how information can be imprinted on the event horizon. The hair is made of soft gravitons and soft photons particles with virtually no energy. The theory suggests that when a particle falls into a black hole, it doesn't just disappear without a trace. It leaves an imprint on the event horizon in the form of these soft particles. The information isn't inside the black hole, and it isn't outside. It's encoded on the boundary. This is one of the most promising potential solutions to the information paradox. The gravitational memory effect we just talked about, the permanent scar in spacetime, is the large-scale consequence of this quantum, soft hair, being imprinted on the horizon. When a black hole swallows a star, the star's information is translated into a unique pattern of soft hair. This pattern subtly alters the surrounding spacetime, creating a specific gravitational memory imprint that radiates outward. So, when the black hole finally evaporates, the Hawking radiation might not be random after all. It could be subtly correlated with the soft hair. As the horizon shrinks, the information encoded in the hair gets passed to the outgoing radiation. The process is incredibly scrambled, but in principle, the information isn't lost. It's returned to the universe, encoded in the faint glow of the evaporating black hole. It seems the universe found a loophole. It respects gravity's rule that nothing escapes, and quantum mechanics' rule that information is never destroyed. It does this by turning the black hole's event horizon into a kind of holographic storage medium, a 2D surface that records the information of everything that fell in. The holographic reality. So, the universe seems to have clever ways to keep records. But these clues from black holes point to an even deeper, more mind-bending possibility about the nature of reality itself. We're now entering more speculative territory, but it's grounded in a powerful concept in modern physics, the holographic principle. First proposed by Gerard T. Hooft and developed by Leonard Susskind, the holographic principle was inspired by black holes. It suggests that all the information contained in a volume of space, like our entire three-dimensional universe, could be encoded on a two-dimensional boundary surface, like a giant hologram. The 3D world we experience might just be a projection of information stored on a flat, distant surface. This sounds like science fiction, but it has a surprisingly solid mathematical foundation in string theory. It also connects to another big idea in quantum gravity, that at the tiniest possible scale, the Planck scale, spacetime itself might not be smooth and continuous. It might be pixelated, made of fundamental, indivisible units. If reality is a hologram, it means that information isn't just something in the universe, it might be the most fundamental thing about the universe. Matter, energy, and even spacetime itself could be emergent properties of this underlying informational code. The universe isn't just like a computer, in a sense, it is one. It's constantly processing the information encoded on its boundary to generate the reality we perceive. This idea is still a frontier of physics, and it's far from proven. But it offers a potential framework where cosmic memory isn't just an odd feature of black holes or gravitational waves, but a fundamental property of reality. It suggests a universe where nothing is ever forgotten because everything is part of the information that makes the cosmos what it is. The human imprint. If we live in a universe that remembers, what does that mean for us? The implications are not just cosmological, they're deeply personal. If every event leaves a physical trace, whether a gravitational scar or an imprint on the holographic boundary of the universe, then the past isn't truly gone. It coexists with the present, written in a language of geometry and quantum states that we're only just starting to read. Your first steps, a forgotten conversation, a quiet moment of joy, these might not just be fading electrical signals in your brain. In a very real, physical sense, the information of their occurrence may be permanently encoded in the fabric of reality. This idea challenges our perception of ourselves. We tend to think of ourselves as temporary arrangements of atoms. But in a universe with memory, every action you take, every choice you make, leaves a permanent imprint on the cosmos. You aren't just a reader of the universe's history, you're a co-author. The record of your life isn't just stored in a fragile biological brain but may be woven into the indestructible structure of spacetime itself. This leads to a profound philosophical question. If every event is recorded and contributes to the evolution of the cosmos, do we truly have free will? Or are our choices simply the universe playing out a calculation based on all the information that came before? Philosophers have debated this for centuries. Perhaps free will and determinism aren't enemies. Perhaps our conscious experience of making a choice is the very mechanism through which the universe turns possibilities into a single, recorded outcome. Our consciousness could be the fine point of the pen with which the universe writes its story. In a universe that remembers, nothing you do is without consequence. Every act of kindness, every moment of creativity is woven into the cosmic tapestry. It's a humbling thought. It suggests a kind of informational immortality. Long after we are gone, the information that constituted you, your experiences, your choices, your impact will persist, encoded in the memory of spacetime for eternity. We began with a question: does the universe remember everything? We've traveled from the edge of black holes to the very fabric of reality, and the answer emerging from the frontiers of physics is a tentative, but mind-blowing, yes. From the permanent scars left by gravitational waves to the informational hair on black holes, we're discovering the universe isn't a blank slate. It's a cosmic archive, a vast, ever-growing repository of every event that has ever occurred. The idea that every action is permanently etched into the fabric of reality is one of the most profound concepts to come from science. It reframes our place in the cosmos. We aren't just fleeting passengers, we are part of a permanent record. Our lives aren't lost to time but are woven into the eternal memory of the universe itself. The story of the cosmos is our story, and it's a story that will never be forgotten. What do you think? If the universe has a perfect memory, does that change how you see your own life and actions? Let us know your thoughts in the comments below. And if you want to explore more of the universe's greatest mysteries, make sure to subscribe and turn on notifications. Part 2. What physicists mean by information. When most of us hear the word information, we think of something human. A sentence in a book, a secret in a letter, a number stored on a phone. We imagine facts, memories, names, messages, things that can be learned, forgotten, copied, or erased. And in ordinary life, that is exactly what information feels like. But the universe seems to use the word in a quieter, deeper way. In physics, information is not just what you know. It is what reality knows about itself. It is the exact description of how something is. The position of a particle, the direction of its spin, the energy it carries, the way it relates to everything around it. Information, in this sense, is not an extra feature added on top of matter. It may be part of what matter is. And that is where this story begins to change. Because if information is truly built into the structure of reality, then every event, even the smallest one, leaves behind more than an impression in a human mind. It leaves a description, a trace, a pattern, something that may continue to exist, even after the moment itself seems to fade. So before we can ask whether the universe remembers everything, we have to understand what it would mean for the universe to remember it all. We have to slow down and ask a strangely simple question. What is information, really? Imagine a single glass of water sitting quietly on a table in a dark room. To you, it is just a glass of water. Clear, still, ordinary. But to a physicist, that quiet glass is an ocean of detail. It contains an enormous number of molecules, each moving in its own way, each with a location, a momentum, an energy, and a relationship to the molecules beside it. If you could somehow know the complete state of every particle in that glass, you would have a detailed description of the system. That description is information, not meaning, not poetry, not memory in the emotional sense.
Just the exact state of what is there. This is one of the most important shifts in the entire subject. Information in physics is not about whether something matters to us. It is about whether the universe can distinguish one state from another. A warm glass of water and a cold glass of water are not the same state. A spinning electron pointing one way is not the same as one pointing the opposite way. A star before it explodes and a cloud of gas after it explodes are not the same arrangement. The difference between those states is physical, and that difference is information. In other words, information is the fine detail of reality. It is the answer to the question, what exactly is going on here? And once you begin to see it that way, the universe starts to look less like a collection of objects and more like a constantly changing library of states. Every object is a pattern. Every event is a transition between patterns. Every moment is a new arrangement of information. That may sound abstract at first, but it becomes surprisingly intuitive. Think of a deck of cards. If the cards are arranged in one order, that is one state. Shuffle them and arrange them differently, and now you have another state. The cards are the same cards, but the pattern is different. The arrangement itself carries information. The universe works in a somewhat similar way, though on a scale far beyond anything we can picture clearly. The particles may still be there. The energy may still be there. But if the arrangement changes, the information changes too. Physics is deeply concerned with those arrangements and with how they evolve over time. This is why information became so important in modern science. Because once physicists realized that the exact state of a system matters, they also realized something else. If the laws of physics are truly lawful, then the evolution from one state to the next should also preserve some trace of what came before. Otherwise, the universe would become partly unreadable. The story of cause and effect would begin to dissolve. And that would be a very strange universe indeed. Long before black holes entered the conversation, information was already quietly sitting at the center of physics. It appears in thermodynamics, where scientists study heat, energy, and disorder. It appears in quantum mechanics, where even a tiny particle must be described not just as a thing, but as a set of possibilities governed by precise mathematical rules. It appears in computing, where bits, yes and no, on and off, become the language by which physical systems can store and transform states. But physics does not treat information as a metaphor. It treats it as something real. There is an old intuition that if you destroy an object, you destroy what it was. Burn a letter, and the words are gone. Smash a vase, and the vase is gone. Grind a book into ash, and the story has vanished. Yet physics invites a gentler, stranger view. The letter burns, yes, but the particles do not disappear. The ink becomes smoke and gases and heat. The paper becomes ash and drifting carbon compounds. The structure changes. The neat pattern becomes wildly scrambled. But in principle, the resulting state still contains a relationship to the earlier one. The information has not necessarily been deleted. It has become dispersed, hidden in a much more complicated form. That distinction matters enormously. Lost to us is not always lost to the universe. This is part of why information feels so mysterious in physics. It lives at the boundary between what is theoretically still there and what is practically impossible to recover. If you burn a page, no one is realistically going to reconstruct every word by tracing every particle of smoke in the room. But the deeper question is not whether humans can recover it. The deeper question is whether the laws of nature have truly erased it. And for a long time, the answer from quantum theory seemed to be no. Not erased, only transformed. That is a much more unsettling answer than it first appears. Because it suggests that forgetting may be more difficult for reality than we imagine. To understand why, we need to move for a moment into the quantum world, where information becomes even more delicate and even more important. In everyday life, objects seem to have definite properties. A ball is here. A lamp is there. A cup is hot or cold. It all feels solid and straightforward. But at the quantum level, the world becomes subtler. A particle is not described only by where it is. It is described by a quantum state, a mathematical object that contains the probabilities of what might happen when we interact with it. That state carries information. It tells us what outcomes are possible and how likely they are. It is, in a sense, the most complete description physics can give. And one of the quiet miracles of quantum mechanics is that these states evolve according to rules that are extraordinarily precise. The equations do not simply throw information away. They carry it forward. This principle is often described through the idea of reversibility. If you knew the full quantum state of a system and could follow its evolution perfectly, then in principle you could run the equations backward and reconstruct what came before. Reality, at that deep level, does not seem eager to lose track of itself. It changes. It unfolds. It becomes more entangled and more complex. But beneath that complexity, the rules preserve structure. This is one reason physicists became so resistant to the idea that information could simply vanish. Not because it felt emotionally unsatisfying, but because it seemed to violate the logic of the laws themselves. A universe that destroys information would be a universe where the past could become fundamentally unrecoverable even in principle. Two different histories could collapse into the exact same present with no way to tell them apart. Cause would become harder to trace. The chain linking one event to the next would start to fray. That possibility unsettled physicists for good reason. The elegance of science depends on the idea that reality has continuity, that the future grows out of the past according to rules, and that those rules do not casually erase the differences between what really happened and what did not. So when information entered physics, it did not enter as a side topic. It entered almost as a safeguard for intelligibility itself. If matter and energy tell us what the universe contains, information tells us how it is arranged. And arrangement is everything. A living cell and a dead cell may contain many of the same atoms, but not in the same order. A functioning brain and an inactive one may be made of similar materials, yet their patterns are profoundly different. A library and a pile of paper can contain the same amount of substance, but not the same informational structure. Meaning, memory, identity, even life itself may depend less on what things are made of than on how they are organized. That idea begins in physics, but it reaches almost everywhere. It also helps explain why information became tied so closely to entropy, a word that often appears whenever people talk about time, order, and decay. Entropy is often described as disorder, though that is only part of the picture. More precisely, entropy measures how many microscopic arrangements correspond to the same large-scale appearance. A neat stack of papers can be arranged in relatively few specific ways. A messy pile can be arranged in vastly more. That is why disorder is more probable. There are simply more ways for things to be messy than neat. And this is where information enters again. When a system becomes more entropic, some of the fine detail that once made its state easy to specify becomes harder to track. The information is not necessarily annihilated, but it becomes distributed across more degrees of freedom, more hidden variables, more microscopic complexity. It sinks into the background. This is why an ice cube melting in a glass feels like a loss of structure. The clean boundary softens. The distinction blurs. The ordered form dissolves into the more probable, more mixed state. It feels like something has been forgotten. And maybe, from the human point of view, it has. But physics is stricter than human intuition. It asks not whether the pattern is easy to see, but whether the full state of reality still contains its consequences. In many cases, it does. A scrambled egg does not turn back into a fresh egg, but the atoms still obey the same laws. The information has become hopelessly mixed for any practical purpose, yet the universe itself has not broken its accounting. It has only made the bookkeeping too complex for creatures like us. That difference between erased and scrambled is one of the quiet themes running under everything that follows. Because black holes, as we will soon see, seem to do something much more severe than scrambling. They seem to erase. And that was the real source of the crisis. But before we go there, it helps to pause and feel how far we have already come. We began with the ordinary meaning of information. Facts, words, memories, things written down. And slowly, we have arrived somewhere much stranger. Information in physics is the exact specification of a state. It is the fine-grained detail of reality. It is the difference between one possible universe and another. It is the pattern hidden inside matter and energy. It is what allows the laws of nature to connect one moment to the next. And once you begin thinking this way, memory itself starts to look different. Perhaps memory is not only what minds do. Perhaps memory is also what reality does when it refuses to collapse all histories into silence. A particle remembers, in its state, how it can interact. A molecule remembers, in its structure, what bonds it can form. A crystal remembers the conditions under which it cooled. A fossil remembers an ancient body through pressure and mineral replacement. Light from distant galaxies remembers events that happened billions of years ago by carrying old information across space. In that sense, the universe is already full of memory. Not emotional memory. Not narrative memory. physical memory, traces, constraints, encoded histories, states that still bear the shape of what came before. Even your own body is full of such memory. The folds of the brain shaped by repetition, the scar on the skin, the DNA passed down across unthinkable spans of time, the chemical signatures of old experiences, the starlight reaching your eyes after traveling for ages through the dark. Everywhere you look, the present carries instructions from the past. Reality does not merely happen, it accumulates. That may be why this question reaches so deeply into human feeling. Because beneath all the mathematics, there is a more intimate fear. What becomes of a moment once it is gone? When a word is spoken and fades into silence, is it finished? When a life ends, does its pattern vanish? When a star explodes in a distant galaxy, does that event truly disappear? When a thought passes through your mind for the last time, is it erased from existence? Physics does not answer those questions in the language of comfort. It answers in the language of states and laws and structure. But its answer is often more haunting than a simple yes or no. It suggests that the universe may not be built to discard detail lightly. It may hide it, diffuse it, scramble it beyond recognition, spread it thin across radiation and dust and quantum states. But outright erasure seems to be something the laws resist. And that is what makes black holes so troubling. Because a black hole looked, at first, like the one place in the universe where this careful conservation of information might fail. A place where all the detail of what fell in could be reduced to almost nothing visible from the outside. A place where history itself might reach an edge and simply stop being readable. That is why information became the heart of the black hole paradox. Not because scientists suddenly became sentimental about memory, but because black holes appeared to challenge one of the deepest habits of the universe, its refusal to forget completely. And maybe that is why this subject has such a peculiar emotional force. At first it sounds technical, almost dry. Information theory, quantum states, entropy, reversible laws. But underneath it is a very old human concern. Whether anything is truly lost. Whether events leave permanent traces. Whether existence keeps a record. Whether the universe, in its own silent way, remembers. By now, we can at least say this much. In physics, information is not a metaphor. It is not just a convenient way of speaking. It is a precise way of describing how reality is arranged. It is the hidden detail that distinguishes one state from another. It is what allows the cosmos to evolve without becoming unintelligible. It is what links cause to effect, moment to moment, pattern to pattern. And once information enters the story, forgetting becomes much more difficult to define. Maybe what we call forgetting is often just distance. Maybe what we call loss is often just dispersal. Maybe what appears gone is only hidden in a form too vast, too subtle, or too scrambled for us to read. If that is true, then memory may be woven far more deeply into the cosmos than we once imagined. Not as a thought, not as a feeling, but as a property of reality itself. And that brings us to the next step. Because if information is this fundamental, if the universe seems so reluctant to destroy it, then what happens when something falls into the darkest objects we know? What happens when information meets a black hole? If you enjoyed drifting through this question with me, you can quietly like the video, subscribe to the channel, and share your thoughts below. I'd love to know what stays with you most, the idea that information is the pattern of reality, or the possibility that nothing is ever fully erased. Part 3. The law that says information cannot be destroyed. There is something deeply comforting about the idea that the universe keeps a kind of account. Not in the moral sense. Not in the sense of reward or punishment. Just in the quiet physical sense that what happens, truly happens, and cannot simply be wiped away without a trace. A glass can shatter. A forest can burn. A star can collapse. A voice can fade into silence. From where we stand, surrounded by endings, it often feels as if reality is full of disappearance. Things break apart. Details slip away. Memories dim. Entire lives seem to sink beneath the surface of time. And yet, as physics developed, scientists began to notice that nature itself behaves as though it is far more careful than we are. Again and again, the laws of the universe seemed to suggest the same strange principle. Things may change form. They may scatter, dissolve, transform, and become almost impossible to reconstruct. But at the deepest level, the underlying information about what they were is not supposed to vanish. This is not merely a poetic thought. It is one of the reasons the black hole paradox became so unsettling. Because by the time black holes entered the story, physicists had already become used to a universe that guards information with almost obsessive discipline. So in this part of the journey, we are going to settle into that principle. Slowly, gently. We are going to explore why modern physics came to believe that information is preserved, what that means in practice, and why the idea is so important. Because before we can understand why black holes seem to threaten the logic of reality, we need to understand the rule they appeared to break. The rule, put simply, is this: the universe can scramble information. It can bury information. It can spread information so thinly across reality that no human mind could ever gather it again. But according to the deepest laws we know, it should not be able to truly destroy it. To feel the weight of that idea, it helps to begin somewhere ordinary. Imagine a sheet of paper lying on a desk. On it is a handwritten note, a few simple sentences, a thought captured in ink. You strike a match and touch the flame to one corner. The paper curls. The edges glow. The note darkens, blackens, and then breaks apart into drifting ash, hot gases, smoke, and heat. To your eyes, the message is gone. No one standing in the room would say otherwise. The note has been destroyed. Whatever was written there has vanished into the air. That is the common sense view, and in daily life it is perfectly reasonable. But physics asks a quieter question. What exactly disappeared? The paper changed form. The ink changed form. Energy was released. Molecules scattered into the room. The neat arrangement that once made the message readable has been violently disrupted. But the particles themselves did not slip out of existence. They continued on, entering new states, forming new patterns, obeying the same physical laws as before. The information in the practical sense is gone. You can no longer read the note. But the information in the physical sense may not be gone at all. It has become dispersed. Some of it is carried in the motion of smoke molecules rising toward the ceiling, some in the thermal vibrations of the air, some in the chemical products left behind in ash, some in the light released by the flame. The original pattern has been shattered and mixed into the environment in an unimaginably complicated way. Yet the deeper laws of motion still connect the before and after. Nature, in principle, still knows what happened. This distinction between erased and scrambled sits at the heart of the whole subject. Human beings are used to practical loss. We lose files. We lose letters. We lose names, faces, and moments. From our point of view, once something becomes too difficult to recover, it is as good as gone. But the universe does not define loss by convenience. It defines it by whether different pasts can still, in principle, lead to distinguishable futures. That is a much stricter standard. And over time, physicists found themselves increasingly committed to it. One reason comes from classical physics, the older framework built by Newton and those who followed him. In that world, if you know the position and motion of every object at one moment, the laws let you predict what happens next. More than that, they also let you run the story backward. If you see the current positions and velocities of every billiard ball on a table, you can infer how they must have moved a moment earlier. The equations do not naturally forget. They evolve states in a lawful way. A present arrangement is tied to a past arrangement, and that present arrangement will in turn generate a future one. The universe may be astonishingly complex, but the equations themselves do not imply casual deletion. They imply continuity. It is true that in practice this becomes impossible almost immediately. A few bouncing balls are manageable. A swirling atmosphere is not. Add enough particles, enough collisions, enough tiny uncertainties, and prediction becomes hopeless. But hopeless for us is not the same as lawless for nature. The complexity belongs to our limitations, not necessarily to the universe itself. Then quantum mechanics arrived and made the question even sharper. In the quantum world, physical systems are described by quantum states. These states contain the most complete information the theory can provide about a system. And crucially, the ordinary time evolution of a quantum state is governed by a kind of mathematical process that preserves that information. Physicists describe this using a technical word, unitarity, but the spirit of it is simple enough. The evolution is reversible in principle. If you had complete access to the quantum state and perfect control over the mathematics, you could evolve it forward or backward without losing the underlying information. Reality may become more entangled, more subtle, and vastly more difficult to interpret, but the bookkeeping remains intact. This was not a minor detail. It became one of the quiet pillars of modern physics. Because if quantum evolution were not information preserving, then the story of cause and effect would begin to fracture. Different pasts could collapse into the exact same future in a final, irretrievable way. The universe would become, at a deep level, less readable. Not just hard to calculate, but fundamentally ambiguous. Physicists are willing to accept many strange things. They have accepted curved spacetime, quantum uncertainty, non-local entanglement, and expanding space. But a universe that simply deletes information without explanation is unsettling in a more structural way. It threatens the coherence of the entire framework. To understand why, think of a library. Imagine a vast library where every book is being continuously rewritten by invisible hands. Pages tear, words rearrange, sentences dissolve into symbols, and whole volumes are translated into other languages you do not know. To you, the order would look like chaos. But imagine that beneath this chaos, there is still a rule. Every transformed page can, in principle, be traced back to what came before. The library is disordered, but not meaningless. Now imagine something worse. Imagine books that do not merely change, but lose pages into nothingness, with no trace of what they once contained. Not hidden, not encoded elsewhere. Truly absent. At that point, the library stops being a transformation of content and becomes something broken. The continuity of the record is damaged. That is roughly why physicists cared so much. They had come to believe that nature behaves more like the first library than the second. The pages may be scattered. The script may become unreadable. The order may be buried under impossible complexity. But the record, somehow, remains. This instinct was reinforced by another major area of science, thermodynamics, which is the branch of physics dealing with heat, energy, and entropy. At first glance, thermodynamics seems to tell the opposite story. It tells a story of irreversible change. Hot coffee cools. Ice melts. Perfume spreads through a room and never spontaneously gathers back into the bottle. Eggs scramble and do not politely unscramble themselves. Everywhere we look, nature seems to move from order to disorder. This one-way drift is tied to entropy. Entropy is often described as a measure of disorder, though a gentler way to think about it is this. High entropy states are states that can be realized in many microscopic ways. Low entropy states are more specific and constrained. There are many ways for a room to be messy, but relatively few ways for it to be arranged with perfect neatness. So left to itself, a system naturally tends to wander toward the more probable possibilities. This feels like loss. Structure blurs. Distinctions fade. Fine detail becomes harder to track. But here too, physics makes a subtle distinction. An increase in entropy does not necessarily mean information has been annihilated. It often means the information has become inaccessible at the level we care about. It has flowed into microscopic detail. It has spread into correlations too small and too numerous for us to monitor. The neat pattern has not been obliterated so much as diluted into a sea of possibilities. That is why a drop of milk dispersing into coffee feels irreversible. In principle, the molecules still obey reversible laws. In practice, the information about their exact arrangement has become dispersed among so many particles that recovering the original state is fantastically unrealistic. Again, the universe may not have forgotten. It may simply have hidden the answer in too many places at once. This is where the topic begins to feel strangely intimate. Because so much of human life is built around the difference between what is inaccessible and what is truly gone, we misplace things. We lose conversations in the noise of old years. We forget faces we once knew well. It is tempting to think that what slips beyond our reach has ceased to exist in any meaningful sense. But physics keeps whispering a different possibility. That hidden is not the same as destroyed. That unreadable is not the same as erased. That the universe may preserve more than we can ever retrieve. This becomes even clearer when we think about collisions and transformations at the particle level. When two particles collide in a controlled experiment, physicists can often predict the distribution of outcomes with extraordinary precision. The details are governed by conservation laws. Energy is conserved. Momentum is conserved. Electric charge is conserved. These laws act like strict accounting rules. The universe does not allow the numbers to drift carelessly. The totals must balance. Information is not exactly the same kind of conservation law in the simple textbook sense, but it begins to feel similar. It belongs to this larger intuition that nature keeps track, that the transition from before to after is not arbitrary. A shattered vase looks nothing like an intact one, but the moment of impact, the direction of the force, the material structure, the resulting fragments, all remain connected by law. The world after the shattering still carries the signature of the world before it. In fact, this is how forensic science works at all. A footprint in mud preserves a body that is no longer standing there. A fingerprint preserves the contact of a vanished hand. Tree rings preserve seasons that passed long ago. Fossils preserve organisms that disappeared millions of years before humans existed. Radiation from the early universe preserves the young cosmos in a faint afterglow we can still measure today. Everywhere we look, reality contains traces. The present is full of records. Sometimes they are crisp enough to read directly. Sometimes they are faint and fragmented. Sometimes they are so scrambled that only mathematics can tell us they still matter. But the universe seems to have a strong habit of carrying the past forward rather than dropping it into oblivion. And that is why the modern idea that information cannot be destroyed feels less like a random doctrine and more like the natural culmination of many lines of evidence. Classical laws imply reversible evolution in principle. Quantum laws preserve the structure of the state. Thermodynamics scrambles, but does not obviously erase. Conservation laws suggest a universe that keeps account with astonishing discipline. Little by little, physicists became accustomed to the thought that information is part of what nature protects. Not in a sentimental way, in a structural way. And once you accept that, something remarkable follows. The universe is not merely a place where events occur. It is a place where events continue to constrain what can happen next. The past remains active, not because it is still visibly present, but because the current state of reality still bears its imprint. What exists now is partly shaped by what existed before. The present is not independent. It is inherited. This is true on the largest scales as well as the smallest. A galaxy remembers the motions that formed it. A planet remembers the violence of its birth in its layers and composition. Your body remembers evolution in the shape of your bones and the code of your cells. Your mind remembers old experiences in patterns of connectivity and chemistry. Even silence in a room remembers what just happened, because the air, the warmth, and the arrangement of things have all been altered, however subtly. The world is full of aftermath, and aftermath is a kind of memory. There is also something quietly radical hidden inside this idea. If information really is preserved, then what we call destruction may often be a human-scale illusion. We name things according to the level at which we live. A house burns down. A voice disappears. A file is deleted. A life ends. These are real endings in our world, and they matter. But physics keeps opening a second perspective, one in which endings are also transformations into states we no longer recognize. The message burned, yet the particles remain. The star collapsed, yet its matter and radiation continue onward. The living brain falls silent, yet the physical traces of its existence have already gone outward into the world in countless ways. None of this solves the emotional problem of loss, of course. Physics is not a substitute for mourning. It does not tell us that every meaningful thing remains accessible in the form we care about. It only suggests that nature is less forgetful than our experience would lead us to believe. And maybe that is part of why this question feels larger than a technical issue. Because behind the physics lies a human ache. Will what happened remain real? Will anything of us endure? Do moments dissolve absolutely, or do they leave marks too subtle for ordinary perception? Science does not answer in the language of comfort. But sometimes its answer is more haunting than comfort would be. It suggests that reality may be very reluctant to let go completely. By now, perhaps you can feel why black holes caused such alarm. By the time Hawking and others were studying them, physicists had already built a worldview in which the preservation of information was deeply woven into the logic of nature. Not perfectly understood, perhaps. Not easy to apply in every situation, but deeply trusted. Then black holes arrived like an exception written in darkness. A black hole seemed to swallow the details of what fell inside. And from the outside, all that remained was a minimal description: mass, charge, spin. All the richness of the original object appeared to be stripped away. Worse still, if the black hole later evaporated through Hawking radiation, and if that radiation was purely random, then the information would not even remain hidden inside forever. It would be gone, not scrambled, not buried, not dispersed in a recoverable pattern. Gone. That was the terrifying possibility. A genuine deletion in the cosmic record. And this was not some minor bookkeeping error. If true, it would force physicists to question one of their deepest assumptions about how reality works. It would mean that the universe, at least in some extreme places, does not merely transform history. It can terminate it. That is why the black hole information paradox mattered so much. It was not just about one exotic object in deep space. It was about whether the universe truly keeps faith with its own past. But before we step fully into that paradox, it is worth resting for a moment in the principle we have uncovered here. The law that says information cannot be destroyed is really an expression of something broader. It is the sense that reality is lawful not only in how it moves, but in how it remembers. The universe does not simply hop from one disconnected moment to another. It carries structure forward. It preserves relations. It allows transformation, but resists oblivion. That does not mean the past stays visible. It does not mean every pattern can be recovered. It does not mean humans can decode every ash cloud, every wave of heat, or every entangled quantum state. It only means the universe may be more faithful to what has happened than we are. More faithful than memory. More faithful than history. More faithful than language. And if that is true, then perhaps every event leaves more of itself behind than it seems. Every falling leaf. Every spoken word. Every particle of smoke. Every human life. Every star collapsing into night. Not preserved in the simple forms we love, but preserved all the same, folded into the next state of the world. If this part of the journey has stayed with you, you can gently like the video, subscribe if you'd like more slow explorations like this, and leave a comment sharing what feels most unsettling or beautiful to you. The idea that information is never destroyed, or the idea that the universe may be carrying far more of the past than we can ever see. And from here, we can continue into the darkest place of all. Because if information is supposed to survive, then black holes should not be able to erase it. And yet, for a long time, they seem to do exactly that. Part 4. Black holes, the ultimate cosmic erasers. If the universe is so careful with information, then black holes seem almost impossible. They sit in the cosmos like a kind of contradiction, quiet from a distance, dark at the center, simple in outline, almost elegant. And yet beneath that stillness is one of the most unsettling ideas in all of science. Because a black hole appears to do something the rest of the universe resists. It appears to take rich, detailed reality and reduce it to silence. A star can explode and still leave light behind. A planet can shatter and still scatter matter into space. A living thing can die and still leave traces, chemistry, structure, consequences. But a black hole seems different. It seems to swallow all of that detail and hide it behind a boundary from which nothing returns. That is why black holes captured the imagination so completely. Not only because they are strange, but because they feel final. They are the closest thing physics has to a true disappearance. And yet, as we settle into them more carefully, they become even stranger than that. Because black holes are not simply cosmic vacuum cleaners or hungry holes torn into space. They are objects predicted by the ordinary equations of gravity. They are what can happen when matter is compressed so intensely that space and time themselves curve inward without relief. In other words, black holes are not mistakes in the universe. They are, disturbingly, part of the design. To understand why they seem to threaten information so deeply, we first have to understand what a black hole really is. And to do that, it helps to begin not with something exotic, but with gravity itself. Gravity is the most familiar of the great forces. It is the reason your body rests against the bed or chair beneath you. It is what keeps oceans wrapped around planets and planets circling stars. In Newton's view, gravity was a force of attraction between masses. But Einstein gave us a more beautiful and more unsettling picture. According to general relativity, gravity is not really a force pulling objects through space. It is the shape of spacetime itself. Mass tells spacetime how to curve, and curved spacetime tells matter how to move. A planet or star bends the geometry around it, and other things follow those curves. That is what we experience as gravity. Most of the time, this curvature is gentle enough to live with. The Earth bends space-time just enough to keep us grounded. The Sun bends it enough to hold the planets in orbit. But if enough mass is concentrated into a small enough region, the curvature becomes extreme. And if it becomes extreme enough, something remarkable happens. There comes a point where not even light can find a path outward. That boundary is called the event horizon. It is one of the most important ideas in this entire story, because the event horizon is not a wall. It is not a solid shell. It is not a surface you could land on like the crust of a planet. It is a boundary in space-time, a threshold. Outside it, paths still exist that lead outward. Inside it, all possible future paths point inward. That is what makes it so eerie. The event horizon is not a place where something dramatic must feel like it happens in the local moment. If you were falling through it, and the black hole were large enough, you might not notice anything special exactly at the crossing point. No flash, no sign, no cosmic alarm, and yet something absolute would have changed. From that moment onward, every possible future available to you would lead deeper in. Not because you are being actively dragged by some invisible hand, but because the shape of spacetime itself has closed behind you. That is why the horizon feels less like an object and more like a verdict. Once crossed, return is no longer part of the geometry. This is already enough to make black holes feel like cosmic erasers. If information falls in and no signal can escape, then from the outside world it seems as though the details have been cut off forever. A chair, a book, a cloud of gas, a star, a spaceship, a person. Whatever falls through the horizon becomes inaccessible to everything beyond it, and not just practically inaccessible. In the old picture, fundamentally inaccessible. That is a profound thing to say. Science usually works by observing, measuring, and inferring. But the event horizon creates a region that is, by its nature, hidden from the rest of the universe. Whatever happens beyond it cannot simply be watched and reported back. The black hole closes a curtain around part of reality. This is one reason black holes feel different from other mysteries. They do not merely conceal because they are far away or difficult to study. They conceal by awe. And beyond that curtain lies the singularity, or at least what classical general relativity predicts as a singularity. This word sounds dramatic, and in many ways it is. A singularity is the point where the equations, as we know them, stop behaving sensibly. Density appears to become infinite. Curvature appears to become infinite. Space and time, in the mathematical description, are driven to a kind of edge. Most physicists suspect that this picture is incomplete, that a deeper theory of quantum gravity would soften or replace the singularity in some way. But for a long time, the classical image was stark and simple. Everything that falls in ends up crushed into an unimaginably extreme state. Whether that image is literally true or only a sign that our equations are breaking down, the emotional effect is the same. The black hole appears to be the place where complexity goes to die. Rich structures descend into darkness. Detailed histories vanish behind the horizon. The outside universe is left with almost nothing to look at. And here we arrive at one of the strangest facts about black holes. From the outside, they seem astonishingly simple. You might imagine that if a black hole swallowed very different things, it would somehow preserve their differences in an obvious way. A black hole made from a star should be visibly different from one made from gas clouds. One that swallowed libraries should be different from one that swallowed mountains or oceans or civilizations. Intuitively, it feels like all those distinct histories should matter. But classical physics seemed to say otherwise. According to the famous no-hair theorem, a black hole seen from the outside can be described by only a tiny handful of properties: its mass, its electric charge, and its spin. That is all. Not the shape of the star that formed it. Not the complexity of what fell in. Not the details of the matter that crossed the horizon. All of that richness appears to disappear from the external description. This was a shocking simplification. It meant that black holes seemed to shave reality down to almost nothing. Throw in a violin, a moon, a poem, a person, a planet, and from the outside the black hole only grows slightly heavier, perhaps a little more charged, perhaps spinning a little differently. The individuality of what fell in is not visible anymore. The details are gone from the external record. This is why black holes earned their reputation as the ultimate cosmic erasers. They do not merely hide objects. They seem to erase distinction. And the more you think about that, the stranger it becomes. Because the universe outside the black hole still behaves as though the object has been simplified to a few numbers. The complexity of the original thing is no longer available to the world. It has been replaced by an almost featureless gravitational presence. Something was there. Then it fell in. Now only mass, charge, and spin remain. It is as if reality itself has been compressed into a summary too short to contain the original story. Even the way black holes form contributes to this sense of finality. Many black holes are thought to form when very massive stars reach the end of their lives. For millions of years, a star balances two competing tendencies. Gravity pulls inward, trying to collapse the star under its own weight. At the same time, pressure from nuclear fusion pushes outward. For a while, these forces balance. The star lives in that tension, shining because of it. But eventually the fuel runs low. The outward pressure weakens. Gravity, patient and relentless, begins to win. The core collapses. In some cases, the outer layers explode away in a supernova, while the inner core becomes a neutron star. But if the remaining mass is large enough, even neutron degeneracy pressure cannot stop the collapse. Nothing known can halt it. The star keeps falling inward under its own gravity until a black hole forms. So a black hole is not only an object of darkness, it is the aftermath of a great failure of support. A star that once poured light into the universe eventually becomes a place from which light cannot escape. There is something haunting in that transition. A radiant object becomes the very emblem of absence. A furnace of information, structure, and history becomes a region defined by concealment. And yet the black hole does not destroy matter in the simple sense. Matter still contributes to the black hole's mass. Energy still matters. Angular momentum still matters. The universe keeps some account. But the detailed structure appears lost to outside access. That is what made physicists uneasy. The black hole did not seem to violate all conservation laws. It only seemed to violate the deeper and more subtle continuity of information. To make this more tangible, imagine throwing an encyclopedia into a black hole. In ordinary destruction, like fire, at least the details are in principle spread into smoke, heat, and ash. The information becomes absurdly difficult to recover, but it is still transformed into the surrounding world. But in the black hole picture, the encyclopedia crosses the horizon and simply stops contributing its detail to anything outside. The outside universe no longer has access to the arrangement of letters, the molecular structure of pages, the exact pattern of ink. All that remains externally is a slightly more massive black hole. The same would be true of a melody, encoded somehow in a storage device, or a lifetime of photographs, or the chemistry of a flower, or the pattern of a human brain. All of that detail seems to sink beyond reach. This is where black holes stop feeling like astronomical objects and begin to feel almost philosophical, because they press on a very old fear. The fear that things do not merely end, but vanish without remainder. That entire histories can fall into a kind of silence so complete that the universe itself no longer bears the marks in any readable form. And black holes made that fear scientific. Of course, there are other eerie features that deepened their reputation. Tidal forces near some black holes can become so extreme that an object falling in would be stretched lengthwise and compressed sideways, a process sometimes described, a little darkly, as spaghettification. Time, too, behaves strangely near the horizon. To a distant observer, something falling toward a black hole appears to slow down, dim, and redshift, never quite seeming to cross the horizon completely. But for the falling object itself, the crossing can happen in finite time. These two perspectives, both valid in their own ways, only deepen the strangeness. From far away, the black hole seems to freeze things at the edge. From the point of view of the falling object, the journey continues inward. Even time cannot agree on a simple description. This is important because it shows that black holes do not merely challenge our intuition about matter. They challenge our intuition about reality itself. They force us to ask which description counts, what it means for an event to happen, and how much of the universe can ever be known from one vantage point. Still, for a long time, one broad conclusion seemed unavoidable. Whatever the exact internal story, black holes appear to remove information from the rest of the universe. And that was already troubling enough, even before Hawking's great discovery complicated everything further. Because there was once a way to make peace with the mystery. One could say, perhaps the information is not destroyed after all. Perhaps it is simply trapped inside forever. Hidden, yes, but still existing somewhere beyond the horizon. That would still be unsettling, but not catastrophic. The universe would have regions of permanent secrecy, but maybe not genuine erasure. This was not entirely satisfying, yet it preserved some hope. If the black hole lasts forever, then maybe the information lasts forever too. Locked away, unreadable, but not gone. For a while, that possibility allowed the deeper problem to remain half asleep. Black holes were strange, but perhaps not fatal to the logic of physics. Perhaps they were merely vaults with no key. But then came the realization that black holes might not last forever. And that is where the darkness became sharper. Because if a black hole could slowly evaporate, and if what escaped carried no meaningful record of what fell in, then the situation would become much worse than simple concealment. Then the black hole would not be a vault. It would be something closer to a shredder. The information would not merely be hidden behind the horizon. It would disappear from the universe entirely when the black hole vanished. That possibility would transform black holes from cosmic prisons into cosmic erasers in the strongest sense. But even before we step into that next stage, it is worth pausing with the black hole exactly as classical gravity first presented it. A region formed by collapse. A boundary called the event horizon. A hidden interior. A fate that points only inward. And an external description so minimal that almost every detail seems stripped away. Mass, charge, spin. That is all the outside world gets. It is a shockingly small remainder for something so rich. And perhaps that is why black holes feel so powerful in the imagination. They resemble a kind of ultimate forgetting. Not the soft forgetting of human memory, where an outline remains and only the details fade. Not the ordinary forgetting of old records, where clues survive in fragments. But a severe, gravitational forgetting, where history crosses a threshold and ceases to speak. That image may not be the final truth. In fact, later ideas suggest the story is more subtle than this. But to understand why the information paradox shook physics so deeply, we have to feel the full force of this older picture first. We have to feel why black holes seemed, for a time, like the one place where the universe might abandon its usual care. Everywhere else, information appeared to transform. In black holes, it seemed to disappear behind a boundary. And if the black hole itself could one day die, it seemed that history might die with it. That is why physicists could not let the issue rest. Because if black holes truly erase information, then the universe is not merely stranger than expected. It is less faithful to its own past than the rest of physics had led us to believe. And once that possibility is opened, everything begins to tremble a little. Cause and effect. Predictability. The continuity of reality from one moment to the next. All of it begins to feel less secure. If this slow journey is helping you settle into the mystery, you can gently like the video, subscribe for more calm explorations of space and reality, and leave a comment sharing what unsettles you most: the event horizon, the singularity, or the idea that a black hole might reduce an entire history to just a few numbers. And from here, we move deeper into the real crisis. Because black holes are strange enough when they simply hide information. But the paradox truly begins when we discover they may not keep it hidden forever. Part 5, The Black Hole Information Paradox. For a little while, there was a fragile kind of comfort in the mystery of black holes. Not comfort in the ordinary sense. Black holes were still terrifying in their silence. They still seemed to swallow stars, light, structure, and history. They still placed part of reality behind a horizon that no message could cross. But there was, at least, one possible way to make peace with them. Perhaps, physicists thought, the information is not destroyed at all. Perhaps it is only trapped. Hidden forever, yes. Locked away behind the event horizon, yes. Beyond the reach of any outside observer, yes. But still existing somewhere inside the black hole's concealed interior. That would be strange. It would be frustrating. It would leave the universe with permanent secrets. But it would not mean that the laws of physics had truly broken faith with the past. The record would still exist. Unreadable, perhaps forever, but not erased. For a time, that possibility allowed the deeper danger to remain just out of sight. The black hole could still be imagined as a kind of cosmic vault. Severe, silent, absolute, but still a vault. Something goes in, and though you will never retrieve it, it remains there in some hidden form. If that had been the end of the story, the paradox might never have become so famous. But the story did not end there. Because in the 1970s, Stephen Hawking made a discovery so strange and so powerful that it changed black holes from mysterious prisons into something much more troubling. He showed that black holes are not completely black after all. They emit a faint kind of radiation. Very slowly, over unimaginable stretches of time, they can lose energy. They can shrink. And eventually, at least in principle, they can evaporate away entirely. That changed everything. Because once a black hole can disappear, the old consolation disappears with it. If the information was merely trapped inside, what happens when the black hole itself is gone? That is the heart of the black hole information paradox. And to feel how unsettling it is, it helps to move through it slowly, step by step, because the paradox is not just a technical inconsistency buried in equations. It is a direct collision between two of the most successful ways we have ever found to describe reality. On one side stands general relativity, Einstein's theory of gravity. This is the theory that gave us black holes in the first place. It describes space-time as a dynamic geometry. Matter curves space-time, and space-time guides motion. It is one of the most beautiful and accurate theories in the history of science. It explains planets, stars, gravitational waves, the expansion of the universe, and the large-scale behavior of the cosmos with astonishing precision. On the other side stands quantum mechanics, the theory of the very small. This is the theory that governs atoms, particles, fields, and the subtle probabilities woven into the microscopic world. It is just as successful in its own domain. Quantum theory has allowed us to build lasers, transistors, modern electronics, and much of the technology that shapes daily life. More importantly, it has survived every serious experimental test thrown at it. These two theories are both masterpieces. And yet black holes seem to force them into conflict. General relativity says black holes can exist. It says matter can collapse so intensely that an event horizon forms, sealing off a region of space-time from the rest of the universe. Quantum mechanics, meanwhile, strongly suggests that information is not supposed to be destroyed. Quantum states evolve in a way that preserves the structure of reality's bookkeeping. They may become scrambled beyond hope, but not deleted. As long as the black hole lasts forever, you can almost pretend these views can coexist. Gravity hides the information. Quantum theory insists it still exists somewhere. The two theories glare at each other from opposite sides of the horizon, but they do not yet come to blows. Hawking changed that. His insight emerged from trying to understand what happens when quantum effects are considered near the edge of a black hole. The details are subtle, and we will explore them more gently in the next part. But for now, the key idea is simple. Empty space is not truly empty in quantum theory. It seethes with fluctuations. Near the event horizon, those fluctuations lead to a faint outward radiation. Over immense timescales, the black hole loses energy and mass. It slowly leaks. And if it keeps leaking long enough, it vanishes. Now imagine the implications. Take a black hole formed from something detailed, a star, perhaps. Or to make the thought experiment more vivid, imagine you throw into it a library, a violin, an old family photo album, a cup of tea, a handwritten letter, a human brain, 1,000 years of records, anything rich in structure and identity. All of those details cross the horizon. From the outside, the black hole settles down into its minimal description: mass, charge, spin. Classical gravity has little more to say. Then the black hole begins, incredibly slowly, to evaporate. So the question becomes unavoidable. When the black hole is gone, where is the information? If the outgoing radiation carries it back out in some hidden, scrambled form, then perhaps information survives after all. But Hawking's original calculations seemed to say something else. They suggested that the radiation was thermal. In other words, it looked random, like heat. It depended only on broad properties like the black hole's mass, not on the detailed identity of what had fallen in. The radiation did not seem to encode the story of the black hole's past meals. It did not carry back the pattern of the letter, the memory of the photograph, the arrangement of the atoms in the violin, or the states of the particles that made the original matter what it was. It was as if the black hole, after swallowing history, returned only featureless noise. And that is where the paradox becomes sharp. Because if the radiation is truly random, and if the black hole eventually disappears completely, then the information is not merely hidden. It is gone from the universe. Not inaccessible. Not scrambled into a subtle pattern. Gone. That conclusion is deeply offensive to quantum theory. It means two different initial situations could lead to the exact same final outcome. Throw one encyclopedia into a black hole or another, so long as the mass, charge, and spin balance out in the same way, and once the black hole evaporates you are left with the same generic radiation. Different histories collapse into one indistinguishable ending. The universe, at that point, has forgotten the difference. And quantum mechanics does not like that. In a quantum world, the distinction between different states matters. It is part of what makes the future intelligible in relation to the past. If distinct states can simply merge into identical final states with no preserved trace, then the logic of quantum evolution begins to fail. The continuity between before and after is severed in a way the theory is not built to accept. This is why physicists took the paradox so seriously. At a glance, it can sound almost philosophical, like a question about memory or cosmic meaning. But underneath that atmosphere, it is brutally concrete. Either the black hole evaporation process preserves information somehow, or quantum mechanics, at least in its familiar form, is incomplete. There is no gentle middle ground where both theories remain unchanged and everything is fine. Something has to give. That is what made the paradox feel almost like a declaration of war inside physics. And it is worth pausing here to notice how unusual that is. Science is full of open questions, but most of them do not threaten the foundations of multiple successful theories at once. The black hole information paradox did. It was not just another loose end. It was a place where two powerful truths seemed to pull reality in opposite directions. Gravity said, information can fall behind the horizon. Quantum theory said, information cannot be destroyed. Hawking's evaporation result seemed to add, and the black hole itself can disappear. Put those three ideas together, and the tension becomes unbearable. Something must be wrong, incomplete, or missing. To understand the emotional force of this, imagine a universe as a great historical record, even if written in a language no human being can fully read. Every event changes the state of reality. Every collision, every birth of a star, every thought in a living brain, every particle interaction, every whisper, every supernova, every collapse, every orbit. The universe moves forward by transforming those states according to law. The present inherits the past. Now place inside that universe a machine that can take a detailed past and reduce it to blank output. That is what a black hole threatened to be. A shredder in the archive. A place where cause no longer leaves a readable consequence. A place where history enters but does not emerge. A place where the distinction between what happened and what might have happened begins to blur beyond recovery. That is more than mysterious. It is destabilizing. Because if the universe can truly delete information in one place, why not elsewhere? And if information can be destroyed, what becomes of the assumption that the world is fundamentally lawful in the way physics had believed? How can the future be fully tied to the past if pieces of the past can simply fall out of existence? This is why some physicists felt that if Hawking's original conclusion were right, then quantum mechanics itself might have to be modified. Perhaps, they wondered, information really can be lost. Perhaps the universe is not as careful as we assumed. Hawking himself defended versions of that view for many years. But many others resisted it with great intensity. Not because they disliked the idea emotionally, but because it damaged too much. Quantum theory's entire structure seemed to resist such loss. And physics, as a discipline, had learned to trust structures that preserved continuity more than structures that broke it. So the community split into camps. Some thought information must somehow escape after all, however impossible that seemed at first. Some thought the information might remain in a hidden remnant, a tiny leftover object after evaporation. Some thought the event horizon itself must store the information on its surface in ways not yet understood. Some thought spacetime, entropy, and gravity all needed to be reinterpreted from a deeper framework. And some entertained the possibility that our ordinary ideas of space, time, and inside versus outside were themselves too crude to capture what black holes are really doing. The paradox became not just a problem, but a doorway. Because once physicists understood how serious it was, they realized that solving it might require something more than a patch. It might require a much deeper theory of reality, one that could unite gravity and quantum mechanics at last. In that sense, the paradox did something extraordinary. It turned black holes into laboratories for the deepest questions science can ask. Questions like these: what is information, ultimately? Where is it stored? Is space itself built from information? Can a surface encode a volume? Is the universe holographic in some fundamental way? Do boundaries matter more than interiors? Is the fabric of spacetime itself an emergent record of deeper relations? These questions sound grand, and they are. But they grew out of something almost painfully simple. A black hole seemed to eat a detailed object and later return only meaningless heat. That simple mismatch shook the foundations. There is also something quietly human about why this paradox lingers in the imagination. At its core is a fear many people already know in softer forms. The fear of being forgotten. The fear that a life, a voice, a love, a thought, or an entire history could be reduced to nothing that remains. The fear that the universe may not keep a faithful record after all. Black holes translated that fear into physics. They made it precise. If the universe allows perfect erasure anywhere, then maybe oblivion is not only an emotional metaphor. Maybe it is built into nature. Maybe some events do not merely pass. Maybe they are truly deleted. That is a chilling thought. And yet the paradox also inspired an opposite hope. Because the more physicists examined it, the more they suspected that the universe might be subtler than it first appeared. Again and again, attempts to solve the paradox hinted that information may survive in ways we do not intuitively expect. On boundaries. In correlations. In extremely delicate patterns spread through radiation. In hidden mathematical structures linking distant descriptions of the same reality. So the paradox did not merely threaten meaning. It also deepened mystery. It suggested that reality may preserve its past, but in a language stranger than classical physics ever imagined. Still, in its raw form, the paradox remains beautifully simple. A black hole forms from matter with detailed information. Quantum effects cause the black hole to radiate. The radiation appears random. The black hole eventually disappears. Where did the information go? That is it. No matter how technical the later arguments become, the beating heart of the paradox is just that sequence. A sequence so clean and so cruel that it continues to shape theoretical physics even now. And perhaps what makes it especially haunting is that it begins with an object that already feels like a symbol of finality. Black holes do not seem like places where stories continue. They seem like places where stories end. So when physics tells us that they may also challenge the survival of information, it feels almost too fitting. Of course, the darkest objects in the cosmos would become the stage on which the universe's memory is tested. But maybe that is exactly why they are so revealing. If reality preserves information even there, then perhaps it preserves it everywhere. And if it fails there, then perhaps the universe is more forgetful than we ever wanted to believe. That is why the paradox matters far beyond black holes themselves. It is a test of whether the cosmos truly remembers in the deepest physical sense, whether history is always carried forward, however scrambled, or whether there are places where the record tears. By now, you can probably feel the shape of the next question rising naturally from all this. If Hawking radiation is the thing that turns a merely hidden mystery into a true paradox, then what exactly is that radiation? How can something escape from a region defined by the impossibility of escape? What does it mean for a black hole to glow, however faintly? And could that glow somehow carry the missing information after all? That is where we go next. Because the next step is to look more closely at the slow leak itself. To watch the black hole, not as a perfect prison, but as an object that quietly radiates into the dark. If this part drew you in, you can gently like the video, subscribe if you enjoy these slow journeys into deep science, and leave a comment with the question that lingers most for you. Is the universe truly incapable of forgetting, or do black holes hint at a deeper kind of erasure? And from here, we move into the faint glow at the edge of darkness. The radiation that should not exist, and the leak that may hold the key to everything. Part 6. Hawking radiation and the slow leak of information. There is something almost impossible about the phrase Hawking radiation. It sounds simple enough when said aloud. Just 2 words. And yet those 2 words contain one of the strangest turns in modern science. Because a black hole, by definition, is supposed to be the place where escape ends. It is the region of spacetime where gravity has curved inward so completely that not even light can get back out. It is the emblem of silence, of concealment, of finality. And yet, according to the laws of quantum physics, a black hole is not perfectly silent after all. It glows. Not brightly. Not like a star. Not in any dramatic, cinematic way. A black hole does not light up the dark like a lantern. Its glow is unimaginably faint, especially for the large black holes we know in the universe. But the fact that it glows at all is extraordinary. It means that the black hole is not a perfectly sealed prison. It means that something is coming back out into the universe, however slowly, however weakly. And once that possibility appears, the whole question changes. Because if black holes radiate, then they lose energy. If they lose energy, they lose mass. If they lose mass, they shrink. And if they shrink long enough, they may eventually disappear. The horizon that once seemed like the final hiding place of information may not last forever. So in this part of our journey, we are going to rest with that strange glow at the edge of darkness. We are going to explore what Hawking radiation is, why it was such a revolutionary idea, how it turns black holes into slowly evaporating objects, and why this faint leak became the center of the information paradox. Because once the black hole begins to whisper something back to the universe, we have to ask what that whisper contains. Is it only meaningless heat? Or is the missing story hidden in it somehow? To approach this gently, it helps to begin with a surprising fact from quantum physics. What we call empty space is not truly empty. In ordinary life, emptiness feels straightforward. An empty room is a room with no one in it. An empty glass is a glass without water. An empty stretch of space, intuitively, should just be nothing. A silent background. A blank between objects. But the quantum world does not allow such clean stillness. Even what we call vacuum, space with no particles in it, is not perfectly calm. It carries restless fluctuations. Fields are still there, even in the absence of particles, and those fields are never completely motionless. There is always a kind of trembling at the foundation of reality, a low-level instability that cannot be smoothed into absolute quiet. This does not mean tiny objects are literally popping in and out of existence in the cartoon version people sometimes imagine. The deeper truth is more subtle. Quantum fields allow temporary fluctuations that give empty space structure and activity. Vacuum is not a blank page. It is more like a page covered in invisible ripples, always shifting, always alive with possibility. That matters near a black hole. Because near the event horizon, where spacetime is curved so severely, those quantum fluctuations behave in a way that changes the whole story. A popular way to picture this is through the idea of particle pairs. Very loosely speaking, the vacuum near the horizon can be imagined as producing pairs of particles and antiparticles. Usually, such fluctuations are temporary. They appear and then quickly cancel or recombine, leaving no lasting effect that would be seen as real radiation escaping into the universe. But near a black hole, the horizon can separate what would otherwise reunite. One member of the pair falls inward, while the other escapes outward. To a distant observer, that escaped particle looks like real radiation coming from the black hole. This picture is useful, as long as we remember it is only a picture. The actual calculation Hawking performed is more elegant and more mathematical than this story suggests. It comes from treating quantum fields in the curved spacetime around a black hole and asking what different observers would count as particles. The result is that a distant observer sees the black hole as emitting thermal radiation, as though the black hole has a temperature. That result was astonishing. Because black holes, once thought to be perfectly dark, suddenly behaved a little like warm objects. Not warm in the ordinary human sense, of course. In fact, large black holes are absurdly cold. But they are not at absolute zero. They are not completely inert. They are quantum objects after all. And once you can assign a temperature to a black hole, something else follows almost immediately. Anything with temperature radiates. A hot stove radiates infrared light. A star radiates visible light and more. Your own body radiates heat. So if a black hole has a temperature, then it should also radiate. That radiation is what we now call Hawking radiation. There is a beautiful irony in this. The darkest objects in the universe turn out not to be perfectly black. The cosmic endpoint of no return turns out to possess a faint, patient luminosity. The ultimate prison leaks. That alone would have been enough to make Hawking's work historic. But the real consequences go further. Because when radiation escapes, it carries energy away. And energy and mass are linked. So the black hole cannot radiate forever without paying a cost. It slowly loses mass. Its horizon shrinks. Its lifetime, though enormous beyond comprehension for astrophysical black holes, is no longer infinite. The black hole can, in principle, evaporate. That word evaporate is wonderfully strange here. We usually reserve it for rainwater disappearing from warm stone, or dew lifting from grass under the morning sun. It is a word of softness, of gradual thinning, of quiet release into the air. And somehow it also belongs to black holes. A black hole evaporates not with drama, but with patience. For a stellar black hole, the process is so slow that it dwarfs almost every timescale familiar to us. The universe itself is around 13.8 billion years old, and yet the evaporation time for an ordinary black hole made from a collapsed star is vastly longer than that. Trillions upon trillions of years, and then still more. So long that language itself begins to lose meaning around the numbers. This is important because it reminds us that Hawking radiation is not something we would see as a visible stream pouring out of black holes in the night sky. For the black holes formed by stars, or the supermassive black holes at the centers of galaxies, the glow is far too faint to dominate over the cosmic background around them. They absorb more than they emit in most realistic environments. Their evaporation is a theoretical certainty, not a practical fireworks show. And still, even as a slow whisper rather than a blaze, the implication is enormous. Because now the black hole is no longer just hiding information behind the horizon. It is changing, aging, leaking, moving toward disappearance. That is why Hawking radiation transformed the black hole information problem from a mystery into a paradox. Before Hawking, one could still say, perhaps the information is trapped inside forever. That would be uncomfortable, but not fatal. The universe would contain sealed archives, regions whose contents remain inaccessible. Strange, yes, but maybe acceptable. After Hawking, that comfort began to dissolve. If the black hole radiates thermally and then evaporates away, what remains of what fell in? To feel why this became so painful for physicists, it helps to look more closely at the nature of the radiation itself. Hawking's original calculation suggested that the outgoing radiation is thermal. That word matters. Thermal radiation is the kind of radiation associated with temperature, with heat, with statistical randomness. A hot object radiates not because it is reciting a story of its detailed internal past, but because it has a temperature. Its radiation is governed by broad properties, not by the fine-grained identity of every particle that gave rise to that temperature. And that seemed to be true of black holes as well. The radiation depended on things like the black hole's mass. Smaller black holes would be hotter and radiate more strongly. Larger black holes would be colder and radiate more weakly. But the fine details of what formed the black hole appeared not to matter. Throw in gas, books, stars, bones, music encoded on a disk, whatever you like. Once the black hole settled down, the outgoing Hawking radiation looked the same for black holes with the same basic external properties. That was the horror at the center of the paradox. The glow seemed too simple, too indifferent, too blank. It was as if the black hole had taken a vast, detailed history and returned only generic warmth. Imagine burning a handwritten journal, but instead of smoke and ash that at least still bear a physical relation to the paper, all that comes out is perfectly featureless heat with no remaining trace of the exact words. Now imagine the journal itself also disappears completely. That is closer to the feeling Hawking's result produced. The black hole seemed to eat structure and give back only temperature. And temperature is not enough to reconstruct history. This is why Hawking radiation became such a profound challenge. It was not merely radiation from black holes. It was radiation that seemed to complete the erasure. A thing falls in. The horizon hides it. The black hole radiates. The black hole shrinks. The black hole vanishes. Only thermal radiation remains. Where, then, is the information? This question became even more haunting because Hawking's discovery also connected black holes to thermodynamics in a deep and elegant way. Before Hawking, physicist Jacob Bekenstein had already made a bold proposal. He suggested that black holes should have entropy. This sounded radical because entropy is usually associated with microscopic internal states, with the number of possible ways a system can be arranged while still appearing the same at a large scale. A cup of hot gas has entropy because there are many microscopic ways the molecules can move while still giving the same macroscopic temperature and pressure. But black holes, at least classically, looked so simple. What could their entropy possibly mean? Bekenstein's insight was that black holes behaved too much like thermodynamic objects to ignore. If you throw matter with entropy into a black hole, and the black hole gains mass and area, then perhaps the black hole itself has entropy, ensuring that the total bookkeeping of disorder still makes sense. Hawking's result gave that idea extraordinary force. Once black holes were shown to have temperature, Bekenstein's entropy was no longer just a suggestive analogy. It became part of a genuine thermodynamic description. Black holes seemed to obey laws resembling the laws of heat and entropy. They had temperature. They had entropy. They radiated. They evolved. And perhaps most striking of all, the entropy of a black hole turned out to scale with the area of its horizon, not its volume. That strange fact will matter greatly later, because it hints that the surface of a black hole may matter more than its hidden interior. It is one of the first clues pointing toward the holographic way of thinking that comes later in the story. But for now, staying with Hawking radiation, the key point is simpler. A black hole behaves like a thermodynamic object. It has entropy. It has temperature. It radiates. And thermal radiation, by its nature, seems to forget detail. That is why the problem became so severe. Hawking's own discovery made black holes richer as physical objects, but also more dangerous to the logic of information preservation. There is another quiet beauty in this. The paradox was not born from sloppiness. It was born from success. Hawking combined the great achievements of modern physics, quantum theory and curved spacetime, and followed the logic carefully. The problem did not appear because someone had made a careless mistake. It appeared because the equations seemed to be telling the truth too honestly. Black holes should radiate. Radiation should carry away energy. The radiation should be thermal. The black hole should evaporate. And that sequence seemed to imply the loss of information. That is what made the paradox impossible to dismiss. Now, over the decades that followed, many physicists came to believe that Hawking's original conclusion about true information loss must be incomplete. Not because the radiation itself was unreal, but because the final interpretation felt too destructive to the principles of quantum mechanics. So the question slowly changed. It was no longer simply, does Hawking radiation exist? On that, the field became broadly convinced. The question became, does Hawking radiation only look thermal at first glance, while secretly carrying subtle correlations that preserve the missing information? That is a much stranger possibility. Because it would mean the radiation is not perfectly random after all. It would mean that hidden inside the apparently featureless glow are delicate relationships, almost impossibly fine patterns, encoding the history of what fell in, not in any simple way, not in a neat readable transcript, but in a scrambled, distributed, deeply quantum way. Imagine hearing what seems like static, only to discover that embedded within it is a message so diffuse and entangled that ordinary listening cannot hear it. That is the kind of possibility physicists began to consider. And once they did, Hawking radiation changed character again. It was no longer merely the leak that threatened information. It became the most likely route by which information might escape. Slowly. Indirectly. In a form almost absurdly difficult to decode. But not necessarily lost. This is where the topic becomes both more subtle and more beautiful. Because the universe may not preserve information in the kind way we prefer. It may not hand the past back to us in recognizable forms. It may not return the letter as a letter, or the star as a star, or the life as a life. Instead, if information survives, it may do so in a scrambled mist of quantum relations, spread across radiation and horizon and spacetime in ways no human memory could love. That is not the same as forgetting, but neither is it the same as remembering in any familiar human sense. The black hole, then, becomes not simply an eraser, and not simply a vault, but perhaps a machine for extreme transformation. A machine that takes rich structure and returns it to the universe only after passing it through the most severe scrambling process known in nature. This idea is both reassuring and unsettling. Reassuring, because it hints that the laws of physics may still preserve their continuity. Unsettling, because continuity may come at the cost of comprehensibility. The past may survive, but in a form so scattered and strange that no ordinary mind could ever call it memory. There is also one more important feature of Hawking radiation worth resting with, because it deepens the emotional tone of the subject. The black hole does not lose itself suddenly. It leaks slowly. That matters. The paradox is not a story of immediate destruction. It is a story of patient thinning, of an object once treated as absolute gradually dissolving into the wider universe. The darkest thing imaginable is not sealed. It is porous in the long run. The horizon, which seemed like the end of communication, becomes part of a much longer conversation between the black hole and the cosmos. A terribly slow conversation, yes. One conducted in whispers colder than almost anything else in nature. But a conversation nonetheless. And perhaps that is why Hawking radiation continues to fascinate so deeply. It turns the black hole from a symbol of final silence into something more haunting. A black hole is still dark, still one of the most extreme objects in existence, still dangerous to intuition. But it is not mute. Over timescales so large they defeat imagination, it gives something back. The question is whether what it gives back is enough. Enough to preserve the logic of quantum mechanics. Enough to save information from oblivion. Enough to let the universe remain faithful to its own past. That is what physicists have spent decades trying to answer. Some of the most important clues suggest that the answer may involve the horizon itself, that mysterious surface where area, entropy, and quantum effects all meet. Some clues point toward the idea that a black hole's boundary may record more than classical gravity ever guessed. Some point toward the universe behaving less like a container of things and more like a system in which surfaces encode interiors. Which is to say, the solution may not lie deep inside the black hole at all. It may lie on its edge. If this calm journey through the physics of darkness has stayed with you, you can gently like the video, subscribe for more slow cosmic explorations, and leave a comment sharing what feels most fascinating to you. The idea that empty space is never truly empty, or the possibility that a black hole's faint glow may be carrying a hidden record of the past. And from here, we move to one of the strangest possibilities of all. That a black hole may store information not in its hidden depths, but on its surface, as though reality itself were writing on the horizon. Part 7. The Holographic Universe Theory. What if the universe does not store reality the way we instinctively imagine it does? When we think about the world, we think in layers and depths. We imagine that what is inside something must be stored inside it. The contents of a room are in the room. The pages of a book are inside the cover. The memories in a brain seem to belong somewhere within the folds of the brain itself. It feels natural to believe that if a thing has volume, then the full description of that thing must somehow fill the volume too. But black holes began to whisper a very different possibility. They suggested that the deepest description of a region of space may not live in its depth at all. It may live on its boundary. That idea is so strange that it almost resists being thought clearly. And yet it became one of the most important ideas in modern theoretical physics. Not because it sounds mystical, and not because it flatters our imagination, but because black holes kept pointing in that direction. Again and again, when physicists followed the logic of entropy, information, and horizons, they found themselves arriving at the same unsettling hint. Perhaps the universe is more like a hologram than a solid container. Perhaps what seems three-dimensional may, in some profound sense, be encoded on a surface. And if that is true, then the universe may remember everything in a way far stranger than simple storage inside space. It may record reality at the edges. It may preserve the story of a volume on a boundary. It may hold the memory of the inside on the outside. So in this part of our journey, we are going to settle into one of the most mind-bending ideas in all of physics. We are going to explore why black holes led scientists toward the holographic principle, what it means to say information might be stored on a surface, and why this idea became one of the most promising ways to think about cosmic memory. To begin, we have to return for a moment to something we touched only gently before. Black holes have entropy. That statement sounds simple now because physicists have lived with it for decades. But when it first appeared, it was deeply shocking. Entropy is usually tied to the number of microscopic ways a system can be arranged. A gas in a box has entropy because its particles can move around in many different patterns while still looking, from a distance, like the same gas. The more microscopic possibilities a system has, the greater its entropy. So when Jacob Bekenstein proposed that black holes should have entropy, he was really saying something much larger. He was saying that a black hole, despite appearing simple from the outside, must somehow conceal an enormous number of underlying states. Otherwise, the thermodynamic story would not make sense. Then Hawking arrived and showed that black holes have temperature. And once a black hole has both entropy and temperature, it becomes impossible to dismiss the idea as a metaphor. The black hole is behaving like a real thermodynamic system. It is not merely like one in a poetic sense. It genuinely seems to obey deep laws relating heat, energy, and entropy. And here is where the weirdness becomes unforgettable. The entropy of a black hole is not proportional to its volume. It is proportional to the area of its event horizon. This is one of those facts that can seem technical at first, but the more you sit with it, the stranger it becomes. For most ordinary things, if you make the object larger, the amount of stuff it can contain grows roughly with volume. A bigger room can hold more furniture because it has more interior space. A larger container can hold more water because it has more capacity inside. So if entropy measures, in some sense, how much information a system can hide in its microscopic possibilities, you might expect it to scale with volume too. But black holes refuse that expectation. Their entropy scales with surface area, not with the amount of space hidden behind the horizon, but with the size of the horizon itself. That is an extraordinary clue. It suggests that whatever information a black hole contains, the fundamental bookkeeping is happening on the boundary, not in the interior volume the way common sense would predict. The horizon begins to look less like a passive border and more like an active screen. A place where information is counted. A place where the deep description of the black hole is somehow written. And once that idea appeared, some physicists began to wonder whether black holes were not a strange exception at all. Perhaps they were revealing something general about the universe itself. Perhaps, in the deepest sense, information about any region of space is limited by its boundary area, not its volume. This is the beginning of the holographic principle. To get a feel for why it is called holographic, it helps to think about an ordinary hologram. A hologram can create the appearance of depth, of three-dimensional form, even though the information producing that appearance is stored on a two-dimensional surface. The depth is not exactly an illusion, but it is not fundamental in the way it first seems. The surface contains the encoding, and from that encoding a richer-looking reality emerges. The holographic principle says something similar, though in a much deeper and more mathematical way. It suggests that the full physics of a region of space may be describable by information stored on its lower dimensional boundary. What seems like a three-dimensional world may be representable in terms of two-dimensional data. That is almost absurdly hard to picture, which is one reason the idea feels so haunting. It does not fit the instincts built by human life. We are creatures of rooms, bodies, objects, distances, and volume. We trust interiors. We trust depth. We feel that what is real must be somewhere inside things. But physics has repeatedly taught us that intuitive pictures are not always the deepest ones. The earth feels still, yet it moves. Time feels universal, yet it bends. Space feels empty, yet it seethes with structure. So perhaps it should not be surprising that depth itself may not be as fundamental as it appears. Still, even by the standards of physics, the holographic idea is radical. It emerged most clearly from the work of Gerard T. Hooft and Leonard Susskind, who took the lessons of black hole thermodynamics seriously. If a black hole's entropy is measured by area, then maybe the maximum information content of any region of space is also bounded by area. That would mean the universe stores less the way a box stores objects and more the way a surface stores code. A boundary could, in principle, be enough? And if that sounds like pure speculation, it helps to know that the idea later gained support from one of the most famous developments in theoretical physics, a mathematical correspondence known as ADS, CFT. The name sounds forbidding, and we do not need its technical machinery here. What matters is the spirit of the discovery. In certain special kinds of spacetime, physicists found a remarkable equivalence. A gravity theory in a higher dimensional space could be exactly described by a quantum theory without gravity living on the lower dimensional boundary of that space. That was stunning. It did not prove that our everyday universe is literally the same kind of hologram in every detail, but it showed, with real mathematical precision, that a holographic description of a world with gravity was not just philosophical poetry. It could actually work. A volume and a boundary could tell the same story in different languages. A world with depth could have a full description written at the edge. And suddenly the black hole clues began to look less like accidents and more like signs of a deeper architecture. This has profound consequences for the question we are following through this entire journey. Does the universe remember everything? Because if the holographic idea is even partly right, then memory in the cosmos may not be stored where we intuitively expect. It may not sit in the hidden interior of things. It may be preserved at boundaries, in relations, in encoded patterns spread across surfaces that define a region. This would mean that the event horizon of a black hole is not just the place where escape fails. It may also be the place where information is written down. In a sense, the horizon becomes a ledger. Not a human ledger, of course. Not a tidy record with words and images and dates. But a physical ledger, where the states of what falls in are encoded in ways subtle enough to preserve the logic of the universe without preserving the simplicity of our understanding. That is one of the reasons physicists became so interested in the surface itself. The horizon no longer looked like a border around mystery. It looked like the memory interface of the black hole. And if that is true, then the idea of soft hair, which we touched on earlier, begins to make more sense. Information may imprint itself on the horizon through delicate quantum states. The black hole may not be bald after all. It may be carrying a pattern on its surface, a kind of informational texture, even though from afar it still looks almost featureless. The deeper lesson, though, is not only about black holes. It is about reality. Because once you allow that information can be encoded on a surface, you begin to wonder whether space itself is less like a container and more like an emergent experience generated by underlying information. Perhaps volume is not the most basic layer of existence. Perhaps it is something that arises when enough encoded relations are organized in the right way. That thought changes the whole emotional texture of the universe. Instead of imagining reality as a giant empty box containing matter, you begin to imagine it as a structured informational system from which space, matter, and even gravity emerge. And if that sounds a little like the language of computation, many physicists have indeed been drawn to similar comparisons. Not because the universe must literally be a computer built by someone, but because information processing offers a useful way to talk about how patterns are stored, transformed, and related. The deepest level of reality may be less about things sitting somewhere and more about relationships being encoded and evolving according to law. In that kind of universe, memory is not an optional extra. It is built into the architecture. The world does not merely contain events. It records constraints, correlations, histories, and transitions. It carries forward what has happened in the form of lawful structure. And boundaries may play a much greater role in that process than human intuition ever guessed. It is worth pausing here, because there is a danger in the holographic principle of letting it become too dreamy. It is a rigorous scientific idea, not a vague slogan that reality is fake or that nothing exists. That is not what the principle says. It does not say the world is an illusion in the ordinary sense. It says that the full description of a physical region may be possible in a lower dimensional way. The reality you experience is still real. Distance still matters. Pain still matters. Stars still burn. Lives still unfold. Gravity still shapes the universe. The question is not whether reality exists. The question is what level of description is most fundamental. And black holes suggest that the answer may lie at the edge. There is something oddly beautiful about that. We tend to think of edges as endings. The shoreline where land gives way to sea. The horizon where the world seems to run out. The boundary of a room. The skin around a body. The edge of a page. But physics sometimes turns edges into places of great importance. A boundary can be where information gathers. A surface can be where laws become visible. What looks like a limit can become a record. For black holes, this reversal is especially powerful. The event horizon first appeared as the place where information is lost from view. But the holographic way of thinking transforms it into the place where information may be encoded most fundamentally. The very thing that looked like an eraser becomes a kind of screen. That reversal is almost poetic. And perhaps that is why the idea has such staying power even outside professional physics. It speaks to something deeper than mathematics alone. The thought that the universe may preserve reality not in hidden depths but on subtle surfaces touches the imagination in a way few scientific ideas do. It suggests that what appears lost may be inscribed elsewhere. That disappearance may be a failure of perspective rather than a failure of existence. That memory may survive at the boundary. If we stretch the idea gently, without abusing it, we can see how it also connects to ordinary experience. So much of life is carried by surfaces and traces. Ink on paper, rings in wood, scars on skin, lines on a face, fossils in stone, light arriving at the eye. Records do not always hide in the depths. Often they sit at interfaces, at points of contact, where one thing meets another. Perhaps the universe itself works that way more than we thought. Perhaps reality leaves its deepest records where systems meet their boundaries. This does not prove, of course, that every event is neatly stored in a way we could ever decode. The holographic principle is not a promise that the universe comes with an accessible replay button. If anything, it suggests the opposite. The record may exist in forms so abstract, so distributed, and so mathematically compressed that no creature like us could ever read it in full. The survival of information is not the same thing as the survival of human meaning in human form. That distinction matters. A holographic universe may preserve everything, but not in the way memory preserves a childhood room or a familiar voice. It may preserve in the way equations preserve, in the way boundary states preserve, in the way deep structure carries forward what surface experience alone cannot see. Even so, there is something quietly consoling in the thought. If the holographic idea is right, then the universe is not sloppy. It is not casually dropping pieces of itself into oblivion. It may be encoding far more carefully than our senses reveal. The world may be stranger than our intuition, but also more faithful, more careful with history, more economical with information, more committed to keeping the record than appearances would suggest. And black holes, once feared as the ultimate destroyers, become the very objects that taught us to suspect this. That may be the most elegant twist in the entire story. The darkest objects in the cosmos did not merely threaten memory. They may have taught us where memory lives, not in the hidden center, not in the singular depth, but on the horizon. And once you begin thinking in that way, a larger possibility opens. Maybe the universe itself is a vast relational structure whose deep information is encoded across boundaries at many scales. Maybe spacetime is not the final layer, but an emergent unfolding of something even more basic. Maybe the feeling of moving through a three-dimensional world is real, yet rooted in informational patterns that do not themselves look like ordinary space. This is where the subject begins to blur into some of the biggest questions physics can ask. What is spacetime made of? Why does gravity exist? What is the true meaning of entropy? Where does geometry come from? How can a surface know the contents of a volume? And if information is the deepest currency of reality, then is the universe itself, in some sense, a memory structure? No one can answer those questions completely yet. The holographic principle is powerful, but it is not the final word. Our own universe is not identical to the simplest mathematical examples. Many details remain unresolved. Physicists are still arguing, refining, testing, and extending the idea. That uncertainty is part of the story too. But even as an incomplete guide, the holographic principle changed the landscape. It gave physicists a new way to think about black holes, a new way to think about entropy, a new way to think about space, and perhaps a new way to think about memory. The world may not simply contain information. It may be made intelligible by information, and that information may live at the boundary, quietly generating the depth we experience as reality. If you sit with that thought long enough, it begins to alter the whole mood of the cosmos. Space becomes less like an emptiness with objects in it, and more like a vast unfolding of encoded relation. The horizon of a black hole becomes less like a curtain and more like a page. The universe itself feels less like a silent void and more like a carefully structured record, written in a language we are still learning to read. If this slow exploration is helping you drift deeper into the mystery, you can gently like the video, subscribe for more calm science journeys, and leave a comment with the image that stays with you most. The black hole horizon as a screen, the universe as a hologram, or the idea that reality may keep its memories at the edge. And from here, we move outward again. Because if information can live on boundaries, then perhaps the universe itself is not merely storing isolated events. Perhaps it is functioning as something even larger, a kind of cosmic memory system, where every interaction leaves a trace in the structure of reality. Part 8. Could the universe be a giant memory system? What if memory is not something that exists only in living minds? What if memory is not limited to brains, thoughts, dreams, or the fragile stories we tell ourselves about the past? What if, in a much quieter and stranger way, the universe itself remembers? Not as a person remembers. Not as a diary remembers. Not with feelings, nostalgia, regret, or longing, but with structure, with traces, with patterns that remain after events have passed, with signals that continue traveling long after their source has changed or vanished. Because once we begin to think of information as something physical, and once we allow the possibility that reality may store that information on boundaries, surfaces, or in deep correlations, a larger question begins to rise very naturally. Maybe black holes are not the only places where the universe keeps records. Maybe recording is what the universe is always doing. Maybe every interaction leaves something behind. Maybe every event alters the structure of reality in some way that does not simply vanish. And if that is true, then the cosmos may not just contain isolated memories. It may function, in some broad and silent sense, like a giant memory system. That idea sounds almost too grand at first, too poetic, too close to metaphor. But the more slowly you look at the world, the harder it becomes to avoid a simple fact. The present is full of traces from the past. Everywhere we look, reality carries forward marks, constraints, echoes, and consequences. The world is not built fresh in each moment. It arrives already shaped by what came before. And perhaps that is what a memory system really is. Not a place where the past sits unchanged, waiting to be replayed in perfect form, but a structure in which what has happened continues to shape what can happen next. To feel this properly, it helps to begin close to home. Imagine standing in an old forest. The trees around you are silent, but they are not blank. Their rings preserve droughts and wet years. Their roots have grown around stones and old buried shapes. Their bark carries scars from insects, lightning, disease, and weather. The soil beneath them remembers fire through charcoal, remembers death through decay, remembers seasons through layers of chemical change. Nothing in the forest is simply present. Everything there is inherited. Or think of a shoreline. Each grain of sand carries a history of erosion, transport, pressure, and breakage. The waves shape the coast, and the coast in turn shapes the waves. The pattern of the shore is not random. It is memory made physical. Not memory in words, but memory in form. The same is true everywhere. A fossil is memory in stone. A scar is memory in skin. A canyon is memory in rock. A language is memory in sound. A city is memory in concrete, steel, and habit. A human face is memory in lines, muscles, expression, and time. Reality is full of aftermath. And aftermath is one of the simplest forms of memory. Once you begin to see that, the idea of a cosmic memory system becomes less mystical and more physical. The universe does not need to think in order to remember. It only needs to preserve the consequences of what has happened. It only needs to ensure that events leave traces, however subtle. It only needs to keep the present connected to the past through law and structure. And in many ways, that is exactly what the universe appears to do. Take light, for example. When you look at the night sky, you are not seeing the universe as it is now. You are seeing records. Light takes time to travel, and so every star, every galaxy, every glowing cloud you see is telling you something about the past. Moonlight is a memory just over a second old. Sunlight is a memory about 8 minutes old. The Andromeda galaxy appears as it was more than 2 million years ago. Distant galaxies carry information from billions of years in the past. The cosmos is not merely visible. It is archived in light. That is one of the most astonishing facts in all of astronomy. Space is not silent darkness occasionally interrupted by objects. It is full of messages still in transit. The universe is continuously sending its past forward. Events do not simply happen and disappear. They radiate outward. They leave. They travel. They continue. A star dies, and its light keeps going. A galaxy collides, and the signal keeps spreading. An atom changes state, and the photon moves on. A black hole merger sends out gravitational waves, and space-time carries those ripples across billions of light years. In that sense, the universe is always leaking memory into itself. And perhaps the clearest example of this on the largest scale is the cosmic microwave background. This faint radiation fills all of space. It is often described as the afterglow of the early universe, and that description is both accurate and wonderfully haunting. When the universe was very young, it was hot and dense enough that light could not move freely. Matter and radiation were tangled together in an opaque plasma. But as the universe expanded and cooled, there came a time when atoms could form, and light was finally able to travel through space without being constantly scattered. That ancient light is still here. It has stretched and cooled over billions of years as space itself expanded, and today we detect it as a faint microwave glow coming from every direction. It is one of the oldest records we possess. Not because anyone stored it deliberately, but because the universe never stopped carrying it forward. The early cosmos is still speaking, and what it says is not simple. The cosmic microwave background is not perfectly uniform. It contains tiny fluctuations, small differences in temperature and density, and those slight irregularities became the seeds of later structure. Galaxies, clusters, stars, planets, and eventually living beings arose from a universe that was not perfectly smooth. In that way, the present cosmos is not just a descendant of the early universe. It is shaped by the tiny patterns encoded in that ancient radiation and the matter it described. The universe remembers its beginning, not as a story, but as a structure still influencing what exists now. That alone is a remarkable thought. But cosmic memory may go even deeper than traveling light, because light is only one kind of messenger. There are also neutrinos, those ghostly particles that pass through matter almost without interacting, carrying information from violent places like the sun's core and exploding stars. There are gravitational waves, ripples in spacetime itself, carrying records of black hole collisions and neutron-star mergers across the dark. There are the chemical abundances of elements, telling us which generations of stars lived and died before our own solar system formed. There is the distribution of galaxies across the universe, tracing ancient patterns seeded long before Earth existed. Everywhere we look, the cosmos is legible because it preserves traces. This is what makes the phrase cosmic memory system feel less like poetry and more like a serious possibility. The universe does not erase itself cleanly. It accumulates. And not only on large scales. Quantum physics adds another layer to this picture, one that is even stranger. In the quantum world, particles can become entangled. This means their properties are linked in ways that cannot be reduced to separate independent stories. If two particles become entangled, the state of one is related to the state of the other, even if they later move very far apart. Entanglement does not allow easy communication faster than light, and it does not mean the particles are secretly sending messages in the ordinary sense. But it does mean the universe can preserve relationships across distance in a way classical intuition does not expect. This matters because memory, at a deep level, is often about relationships. A memory is not just a thing sitting by itself. It is a preserved correlation between what happened before and what exists now. In that sense, entanglement begins to look almost like a microscopic form of cosmic record keeping. Interactions leave systems correlated. Past contact leaves present structure. The universe remembers through relation. That is a subtle idea, but perhaps one of the most important in the whole subject. We often imagine memory as storage, as if reality were a giant shelf and every event were a book placed upon it. But physics suggests a more fluid picture. The record of the past may not live in isolated objects. It may live in the way systems constrain one another, in the way states remain linked, in the way one thing carries the consequences of contact with another. A collision remembers itself in the altered motion of the colliding bodies. A measurement remembers itself in the changed state of the measuring device. A star remembers the earlier generations of stars through the heavy elements it contains. A planet remembers ancient impacts in its craters. A molecule remembers its formation conditions in its structure. A life remembers its ancestry in DNA. The universe may not be storing memory in one place. It may be distributing memory everywhere. And that distribution is important, because it helps explain why the past can be so hard to reconstruct even if it is not truly erased. Records can survive in scattered form. Traces can persist without remaining simple. Information can be spread so widely across systems that no single local observer could gather it all again. In human life, we know a gentler version of this. Think of a person who has died long ago. Their voice may be gone. Their thoughts may no longer be accessible. But traces remain. A photograph. A phrase they once repeated. Habits inherited by children. Changes they made to a room, a family, a city, a life. Even when the living memory of a person fades, the consequences of their existence continue outward in distributed form. The universe may operate similarly, though on a much larger and less sentimental scale. Nothing remains exactly as it was. But what has happened continues to shape what is. That is why memory in physics is so different from memory in human experience. Human memory is selective. It distorts. It softens edges. It invents. It forgets. It clings to some moments and loses others. Cosmic memory, if we can call it that, is colder, more impartial, less interested in meaning, more committed to structure. It does not care what we found beautiful or unbearable. It simply carries forward the physical consequences. And yet there is something moving about that too, because it suggests that the universe may be less forgetful than we are. We lose names. The universe keeps signatures. We lose moments. The universe keeps consequences. We lose stories. The universe keeps structure. This brings us to a deeper question. If every event leaves a trace, does that mean nothing is ever truly gone? The careful answer is more complicated than a yes or no. Events pass. Forms dissolve. Patterns break apart. Stars die. Organisms decay. Buildings fall. Human memories vanish. There is no reason to pretend otherwise. The universe is full of transformation and loss. But loss does not always mean total erasure. Often it means redistribution. Often it means that a pattern no longer survives in the form we can recognize, even though its effects have gone outward into other forms. A campfire goes out, but the heat entered the air. A word fades, but pressure waves changed the room. A life ends, but its matter, energy, and influence continue. A star explodes, but its elements seed future worlds. A black hole swallows matter, yet perhaps the horizon and radiation still preserve the information in ways we barely understand. So perhaps the better question is not whether the universe keeps perfect memory in any simple human sense. Perhaps the better question is whether the universe ever stops carrying the consequences of what has happened. And the answer to that seems, more and more, to be no. Reality keeps inheriting itself. This is why some physicists and philosophers have been drawn to the idea that the universe behaves less like a collection of isolated things and more like a vast web of records, constraints, and correlations. A thing is what it is partly because of how it came to be. The present state of the cosmos is not independent. It is the accumulated result of earlier states. That may sound obvious at first, but it becomes profound when fully felt. It means the past is not somewhere else. The past is folded into the present, not intact, not preserved in a neat museum, but active, structural, and unavoidable. Every atom in your body carries a stellar history. Every breath you take interacts with ancient processes older than humanity. The iron in your blood was forged in stars that died long before Earth formed. The carbon in your cells passed through other living systems, oceans, atmospheres, and rocks. Even your consciousness, however mysterious it remains, arises in a brain shaped by genetic inheritance, childhood experience, and constant interaction with a world that was already ancient when you arrived. You are not separate from cosmic memory. You are one of its current expressions. And that thought can be taken outward as well as inward. The universe may remember not by storing tiny exact replicas of events in some hidden vault, but by ensuring that nothing happens without joining the chain of what comes next. In that sense, memory is not a special compartment in reality. It is reality's continuity with itself. A beautiful phrase for that might be this: the universe remembers by refusing to begin from nothing in each moment. Every moment inherits. And once you say that, something else becomes visible. If the universe is a memory system, it is not one built for comfort or readability. It is not designed to hand the past back to us in gentle forms. It is more like an immense physical fabric in which traces are woven into subsequent states. Some of those traces are obvious, like fossils or light from distant galaxies. Some are subtle, like entanglement or the informational structure of horizons. Some may be so deeply scrambled that they survive only in principle, beyond any realistic hope of recovery. But hidden is not the same as absent. That distinction keeps returning because it may be the most important one. A thing can be unreadable without being erased. A record can be dispersed without being destroyed. A memory can survive as influence rather than image. And perhaps this is why the question of cosmic memory touches something so human. Because beneath the physics is an old emotional wish. The wish that what has happened truly happened. That joy mattered. That pain mattered. That nothing meaningful simply slips through reality without leaving a mark. Science does not answer that wish the way religion, poetry, or personal memory might answer it. It answers in colder terms. It says that events alter states. That information constrains futures. That traces propagate. That the present bears the imprint of the past. But even in those colder terms, there is something quietly powerful. The universe may not care in the way we care, but it may still keep the record. And if that is so, then perhaps every event, from the smallest quantum interaction to the death of a galaxy, becomes part of an ongoing cosmic inheritance. A whisper in a room changes the air. A thought changes a brain. A choice changes a life changes others. A star changes chemistry. A supernova changes planets not yet born. A black hole merger changes spacetime itself. Nothing happens alone. Nothing stays isolated. Everything enters the fabric. By now, the image of the universe as a giant memory system may feel less impossible than it did at the start of this part. We are surrounded by evidence that reality carries forward what has happened. Light, matter, geometry, entropy, radiation, and correlation all seem to participate in this larger continuity. The cosmos may not remember with intention, but it may remember with structure. And perhaps that is enough to change how we see the world. Because once you begin to notice traces everywhere, existence starts to feel less disposable. The present no longer looks like a thin surface floating above oblivion. It looks like the latest layer in a deep and accumulating record. You are not standing in a universe that resets every second. You are standing in a universe that has been keeping itself, reshaping itself, and carrying itself forward from the beginning. If that is true, then forgetting is never simple. It may happen for minds. It may happen for civilizations. It may happen for archives and names and languages. But for reality itself, the story may be different. Reality may not forget by default. It may transform. And from that thought, a more personal question begins to emerge. If information is never fully erased, if traces endure, if every event joins the long memory of the cosmos, then what does that mean for us? For our lives, our actions, our brief and fragile existence inside such a vast system? That is where we go next. Because the next step is not just cosmic, it is personal. If this slow exploration is helping you unwind, you can gently like the video, subscribe for more calm science journeys, and leave a comment sharing what feels most striking to you. The universe preserving its past through light, through structure, or through the quiet consequences that never fully disappear. And from here, we move to the most human part of the question. If the universe never fully forgets, then perhaps nothing we do is ever entirely lost. Part 9. If information is never lost, nothing is truly forgotten. There is a quiet difference between being gone and being unreachable. In ordinary life, those two things often feel the same. A voice fades from memory, and to us it is gone. An old letter is lost, and it is gone. A childhood room is changed, an object breaks, a person dies, a star burns out, and everything in us says the same word: gone. It is one of the simplest words we have, and one of the heaviest. But the deeper we travel into physics, the more that word begins to soften at the edges. Not because loss is unreal, not because change can be denied, and not because science offers some easy emotional comfort. It does not. What it offers instead is something stranger. It suggests that reality may not be built to erase as cleanly as it appears to erase. It may allow forms to vanish while traces remain. It may allow patterns to dissolve while consequences continue. It may let stories become unreadable without letting them become absolutely nothing. And if that is true, then the old human fear of being forgotten begins to touch something much larger than psychology. It becomes a question about the structure of the universe itself. Because if information is never truly lost, then perhaps forgetting is not as final as it feels. Perhaps the universe does not preserve things in the way a mind preserves them, or a photograph, or a written name. But perhaps it preserves them all the same, in the only language it has ever really spoken, the language of physical state, relationship, consequence, and trace. So in this part, we turn gently toward the most personal side of the whole mystery. If the universe remembers in some deep physical sense, what does that mean for us? For a life, for a choice, for a passing thought, for a person who fears disappearing, for the ordinary ache behind the question, will I be forgotten? To begin, it helps to admit something simple. Human beings do not really fear physical destruction in the abstract. What we fear more deeply is erasure of meaning. Not only the body ending, but the sense that everything about us could vanish as though it had never happened. We fear that our lives might dissolve into silence. That what we loved, what we suffered, what we built, what we hoped, what we tried to say, and what we failed to say, might all disappear without remainder. This fear is older than science. It appears in graves and monuments, in songs and prayer, in family names and stories passed to children, in the urge to write, to paint, to build, to leave something behind. Even the smallest acts of preservation carry this feeling. Saving a photograph, keeping a watch that belonged to someone gone, repeating an old phrase exactly the way they used to say it, holding onto an email, a shirt, a recipe, a room. We do these things because we know how easily the visible world changes. And because, somewhere beneath that, we do not want the record to end. Physics does not usually speak in such emotional terms. It does not ask whether a life mattered in the way a grieving person asks it. It asks colder questions. What state did the system occupy? How did it change? What traces remain? What information was carried forward? But now and then, those cold questions drift close to the old human ache. And when they do, they become unexpectedly powerful. Because the universe may not answer the fear of forgetting with affection, but it may answer it with continuity. A life is not only a private experience sealed inside a skull. A life is also an event in the physical world, a pattern of matter and energy, a chain of actions, a field of consequences. Your voice moves air. Your decisions alter environments. Your presence changes the chemistry of rooms, the architecture of routines, the emotional states of others, the trajectories of relationships, the flow of time inside a household, a street, a family, a workplace. Even in purely physical terms, you are not isolated. You are continuously imprinting yourself on the world around you. That imprint does not stop because human memory fades. It only changes form. Think of something very small, a hand touching a table. It seems trivial. The contact lasts a second, but it alters things. Heat transfers. Microscopic oils remain. The table's molecules shift ever so slightly under pressure. The air nearby changes. Your own body changes too. Muscles contract. Neurons fire. A choice has become part of the state of the world. Now extend that from one touch to a whole day, then to a year, then to a life. The world after you is not the world before you. And that difference is not imaginary. It is physical. This is one of the reasons the idea of informational survival feels so haunting. It suggests that existence is not as disposable as it seems. Events do not pass through reality like shadows through empty air. They alter the state of things. They join the chain. They become part of what future moments must inherit. In that sense, to have existed at all is already to have entered the memory of the cosmos. Not as a biography. Not as a neat story with your name attached, but as structure. A structure that continues outward. This becomes clearer when we look at how much of the world around us is made of preserved influence rather than preserved form. A river remembers mountains that no longer stand as they once did. A language remembers tongues and migrations from people long dead. A city remembers old economies, old violence, old dreams, old plans, old mistakes. A child remembers parents not only in conscious memory, but in posture, tone, reflex, fear, humor, and habit. A culture remembers through rituals whose original reasons may be forgotten. A species remembers through genes. A landscape remembers through scars, layers, and erosion. A planet remembers through craters and atmosphere. A star remembers earlier cosmic history through the elements it contains. Nothing remains exactly itself forever. And yet the world is dense with inherited shape. That may be the key distinction. Perhaps nothing is truly forgotten does not mean nothing ever changes. It means change does not happen without leaving a record. This is subtler than immortality in the ordinary sense. It does not mean that a person remains preserved as a person in some accessible archive of the universe, waiting to be replayed like a perfect recording. Physics gives us no simple reason to believe that. A mind is a delicate organization. A life is lived in time, not merely in matter. When those patterns dissolve, something real is lost in the human sense. We should not pretend otherwise. But loss of form is not the same as loss without consequence. That difference matters more and more the longer you think about it. A song played in a room ends. The form is gone, but the room is not exactly the same after. The listeners are not the same. Their bodies have changed, their attention has been guided, their emotions shifted, their later thoughts subtly shaped. The event is over, yet it persists in distributed consequences. A conversation ends. The words vanish into silence. But maybe someone sleeps differently because of it, or forgives, or leaves, or stays, or chooses courage, or chooses caution. One event enters another, and then another, and then another, until the original moment is no longer visible yet still active inside the pattern of the world. This is how reality often remembers, not by preserving an image, but by preserving influence. And influence is a form of memory. It may even be the most common form. When physics says information may not be destroyed, this does not necessarily mean every detail remains recoverable by us. Much of it may become hopelessly scrambled. It may disperse into heat, radiation, complex environmental interaction, quantum correlations too delicate to reconstruct, or causal chains too vast to follow. The universe's memory may be exact in principle while remaining inaccessible in practice. That is both comforting and unsettling. Comforting, because it suggests that what happens is not casually erased. Unsettling, because preservation does not guarantee comprehension. The universe may remember more than we can ever read. And perhaps that is true of our lives as well. You may never know how many things you changed simply by being here. A sentence you barely remember saying may have stayed with someone for 20 years. A kindness you thought was small may have altered a life. Even your injuries may echo outward in ways neither you nor anyone else can map completely. Humans tend to measure significance by visibility. We assume that if an effect is not obvious, it must not be real. But the universe does not share that bias. Reality is full of hidden causal threads, quiet inheritances, and subtle long-term consequences. A life may be far more physically and historically entangled with the world than it appears from within. This becomes especially powerful when you think about the ordinary fear behind the question of being forgotten. When people ask, "Will I be forgotten?" they are often not asking whether someone somewhere will remember their name. They are asking whether their existence truly entered the world, whether it left anything behind that remains real, whether love mattered, whether pain mattered, whether being here made any difference once the immediate witnesses are gone. Science cannot answer that in the emotional language we might wish for. It cannot promise that your favorite song, your private grief, your tenderness on a Tuesday afternoon, or the exact texture of your consciousness is archived in a form the universe will hand back someday. But it can suggest something else. It can suggest that nothing you do is self-contained, that every act joins the web, that the state of the universe after you contains the fact of you. That to exist is already to have entered the record. There is a humbling beauty in that. We are used to thinking in human scales. A few decades, a few generations, maybe a century if stories are carefully preserved. Beyond that, names blur, faces vanish. Most people who ever lived are not individually remembered by history. Human memory is narrow, local, and selective. It is full of unfairness. Some are commemorated for centuries. Most disappear from the public record almost immediately. And yet public remembrance is not the same as cosmic remembrance. History forgets all the time. Reality may not. That does not make the human pain of being forgotten disappear. But it changes the frame. It suggests that being omitted from memory is not the same as being omitted from existence. The universe does not depend on monuments to keep a record. It keeps a record through state, consequence, and transformation. You spoke, and the air changed. You loved, and another nervous system changed. You built, and a structure changed. You suffered, and your body changed. You endured, and your choices changed the future. You lived, and the universe after you became different from the universe that would have existed without you. This is not metaphor. It is physics. There is also something deeply challenging in this idea. If nothing is truly forgotten, then not only beauty but harm remains in the record as well. Every cruelty, every injury, every act of neglect, every small betrayal, every violence. The cosmos is not preserving only what flatters us. It is preserving consequence itself. A universe that remembers is not a sentimental one. It is exact. It keeps the imprint of kindness and the imprint of damage alike. That can feel severe. But perhaps there is also an ethical weight in it. If our actions truly enter the structure of reality, then nothing we do is merely private in the deepest sense. Even our smallest choices ripple outward. We do not simply pass through the world. We alter it. We write ourselves into it. And the writing continues beyond our awareness. This does not mean every action has huge visible consequences. Most do not. The universe is not a melodrama where every glance changes history in spectacular form. But it does mean that causality is real, and that reality keeps what causality produces. In a world of informational continuity, actions do not vanish. They become part of the inheritance of later states. This can make life feel heavier, but it can also make it feel more meaningful. Not performatively meaningful. Not in the sense that every moment must be grand. Quite the opposite. It means even quiet moments matter because they too enter the chain. The tone of your voice. The patience you do or do not offer. The way you speak to a child. The way you leave a room. The way you respond when tired. The way you treat someone no one else is watching. All of it becomes part of the architecture of what happens next. In a forgetful universe, maybe such things would disappear. In a universe that preserves information, they do not disappear so easily. This is perhaps the most intimate way science brushes against existential meaning here. It does not tell us that we are eternally remembered as selves in the way religion or hope might imagine. But it tells us that existence is not without inscription. That the universe is not a clean slate refreshed each instant. That what happens is not unmade simply because it passes. A childhood is gone, yet its consequences remain in an adult body and mind. A civilization falls, yet its metals, roads, stories, seeds, and wounds remain in later worlds. A star dies, yet its elements become planets and blood. A person disappears from photographs and family memory, yet the world they altered keeps moving in part because they were there. Perhaps this is a kind of informational afterlife, though not one that belongs to comfort. It belongs to continuity. And continuity may be more fundamental than permanence of form. When we ask whether nothing is truly forgotten, maybe we are really asking whether reality honors occurrence. Whether it keeps faith with what has happened. Whether the past, once real, remains real in its consequences. Whether existence is allowed to count. Physics increasingly suggests yes. Reality seems reluctant to betray its own history completely. Even when forms dissolve, traces remain. Even when patterns scramble, relations survive. Even when memory fails in minds, the universe carries forward altered states. This does not solve grief, of course. A person who has died is still absent. A lost time is still lost. A forgotten face is still gone from conscious memory. No equation softens that directly. But it may slightly alter the loneliness of it. Because absence is not annihilation in the deepest physical sense. The life happened. The love happened. The suffering happened. The kindness happened. And reality has been different ever since. There is another layer to this too, one that black holes pushed into focus. If even the most extreme objects in the universe may not truly erase information, then perhaps the cosmos is more faithful than we assumed at its darkest edge. If black holes do not destroy the record, then the case for informational continuity becomes stronger not at the easy places, but at the hardest place imaginable. The most severe test of forgetting turns into another argument against total erasure. That is almost breathtaking when you sit with it. The universe may preserve itself even through darkness. Which means the question, will I be forgotten, might need to be answered on two levels. Yes, perhaps, in the human sense. Names fade, stories shorten, photographs are lost, generations pass. But no, perhaps, in the physical sense. Nothing that happened can unhappen. No existence leaves the universe untouched. No life, however quiet, fails to enter the structure of what comes after. And maybe both are true at once. Human forgetting is real. Cosmic forgetting may be much rarer. That tension is part of what makes this topic so moving. We are creatures who long for narrative remembrance, yet we may inhabit a universe whose deepest form of remembrance is structural rather than narrative. The cosmos may not keep our stories the way we tell them, but it may keep the fact that they occurred, woven into matter, energy, radiation, relation, geometry, and consequence. In other words, the universe may remember not the way a parent remembers a child, but the way reality remembers a cause. That may sound colder, but it is also astonishingly honest. Perhaps nothing is truly forgotten because nothing real ever becomes unreal. It becomes distant, distributed, transformed, hidden, re-expressed in other states. But what happened has happened, and that fact remains built into what the universe is now. This idea may also change the way we see our own importance. Not in the grand, ego-driven sense. Quite the opposite. It suggests that we matter not because we are the center of the story, but because we participate in it fully. We are made of inherited traces and we produce new ones. We are temporary forms inside an ongoing memory structure much larger than ourselves. You are not outside the cosmos asking whether it will remember you. You are one of the ways the cosmos is remembering itself. That is a startling possibility. Your body carries ancient elements. Your mind carries ancestral pattern and lived experience. Your choices enter the future. Your existence links old matter to new consequence. You are not only observed by the universe. You are one of its events. And events do not vanish cleanly. They propagate. By now, perhaps the question has changed shape a little. It is no longer only, does the universe remember everything? It becomes, what would remembering even mean for a universe? Not names carved in stone, not personal archives, but continuity of consequence, preservation of distinction, refusal to erase what has truly occurred. If that is the right frame, then nothing is truly forgotten, not because everything stays visible, but because visibility was never the deepest measure of survival. A thing may be unseen and still active. A trace may be unreadable and still real. A life may be unremembered by history and still present in the state of the world. That is where this part of the journey comes to rest. Not on certainty. Not on a sentimental promise. But on a quieter and perhaps stronger thought. That the universe may be less careless with our existence than it appears. That reality may not throw away what has happened. That the fact of your life has entered the structure of the cosmos in ways far beyond what any human record can hold. If this part stayed with you, you can gently like the video, subscribe for more slow explorations like this, and leave a comment sharing which idea lingers most for you. That influence is a form of memory, that the universe keeps consequences even when names are lost, or that nothing real ever becomes entirely unreal. And from here, we move into the final part. Because after all the physics, all the paradox, and all the quiet implications, one last question remains. What kind of memory is the universe, really? Part 10. The Quiet Memory of the Cosmos. By now, the question no longer feels quite as simple as it did at the beginning. Does the universe remember everything? At first, it sounds almost like a poetic thought experiment, the kind of question that belongs to late-night wonder more than to science. It feels broad, maybe even impossible to answer. But slowly, as we followed the trail through information theory, black holes, entropy, Hawking radiation, holography, and the strange persistence of physical traces, the question changed shape. It became less sentimental and more precise. Not, does the universe remember the way a mind remembers? Not, does it keep a perfect little archive of our stories in some hidden vault? But something quieter, and perhaps stranger. Does reality preserve what has happened in the structure of what it becomes next? And by the time we reach this final part, the answer emerging from modern physics is no longer a clean yes or no. It is something softer, more careful, more unsettling, more beautiful. The universe may not remember in a human way, but it may remember in the only way a universe can, through state, through relation, through consequence, through structure, through the refusal of the past to vanish without entering the present. That is the quiet memory of the cosmos. It is not emotional. It is not narrative. It does not sit somewhere like a book on a shelf. And yet it may be real all the same. When human beings think about memory, we usually think about images and feeling. A childhood room, a face, a voice, the smell of rain on warm ground, a sentence someone said years ago that somehow never left us. Human memory is intimate, selective, fragile. It brightens some moments and abandons others. It rearranges. It edits. It protects us and betrays us. It is full of tenderness and distortion at the same time. Cosmic memory, if such a thing exists, is nothing like that. The universe does not sit in reflection. It does not feel nostalgia for old stars or grief for vanished worlds. It does not look backward with sorrow or gratitude. It simply carries forward the consequences of what has occurred. It preserves traces where law allows traces to remain. It transforms events into altered states. It lets light travel. It lets matter inherit. It lets geometry keep scars. It lets horizons encode. It lets radiation disperse information into the dark rather than throwing it into absolute nothing. This is a much colder kind of memory, but perhaps also a deeper one, because it does not depend on attention. Human memory fails all the time because attention fails. We forget what we do not repeat. We lose what no one writes down. Whole lives disappear from public records simply because no one remained to say the names often enough. Human history is uneven that way. It remembers emperors and forgets farmers. It remembers wars and forgets quiet tenderness. It remembers what was written, funded, carved, and retold. It forgets countless inner worlds completely. But the universe is not choosing what to remember. That may be the most important difference. It is not biased toward the dramatic. It is not selective in the human sense. It does not preserve only what seemed important to us. It preserves through physics. A collision leaves altered motion. A star leaves elements. A life leaves consequence. A black hole leaves questions, and perhaps also encoded traces. A gravitational wave leaves a subtle scar in spacetime. Ancient light continues across billions of years. The present continues to inherit what came before. The cosmos, then, may be a memory without a storyteller. And that is a strange thing to contemplate, because so much of what we call meaning depends on stories. We want memory to come with shape, with sequence, with recognition. We want there to be someone who knows what happened, someone who understands it, someone who can say, yes, that moment was real, that life was lived, that joy happened here, that suffering happened here, that this mattered. Physics does not speak that way. It does not say your life mattered because it was witnessed. It says your life mattered because it altered the state of the world. That may sound impersonal at first, perhaps even disappointing. But the more quietly you sit with it, the more extraordinary it becomes. Because it means reality does not require applause to keep a record. It does not require remembrance ceremonies. It does not require names carved into stone. What happens enters the structure of the universe whether or not anyone later tells the story. Existence itself is inscription. To have happened at all is already to have entered the fabric. That is one of the deepest ideas hidden in this whole journey. The universe may not be a place where events occur and then vanish. It may be a place where events occur and become part of everything that follows. And perhaps that is what the phrase quiet memory of the cosmos really means. Not a cosmic mind thinking about the past, but a cosmos in which the past continues to live inside the architecture of the present. Once you begin to see memory in that way, the entire universe starts to look different. The night sky becomes a library of delayed light. A fossil becomes not just a remnant, but a message. A black hole horizon becomes not just a boundary, but a possible page. Entropy becomes not simple destruction, but the dispersal of detail into harder-to-read form. Even silence becomes less empty, because silence too is full of altered air, thermal traces, fields, and histories. Nothing stands completely alone. Nothing arrives without inheritance. Nothing leaves without leaving something behind. That does not mean everything remains accessible. This distinction matters more than ever in the final part of the story. The universe may preserve information, but preservation is not the same as readability. A trace may survive while remaining forever beyond recovery. A record may exist without being decodable by any mind inside the system. A life may alter the world irreversibly while leaving no simple narrative behind. The universe may remember, but it may remember in forms too vast, too distributed, too scrambled, or too abstract for creatures like us to fully understand. That is not a failure of the universe. It may simply be the price of scale. Human beings live in a narrow band of reality. We evolved to notice moving shapes, familiar voices, danger, warmth, faces, patterns that help bodies survive. We did not evolve to read the full informational structure of the cosmos. We cannot look at drifting thermal radiation and intuit the microscopic history hidden in it. We cannot stand at the edge of a black hole and decode the horizon. We cannot walk through spacetime and see every causal scar. Our senses are beautiful, but small. Our minds are powerful, but local. So when we say the universe may remember everything, we should be careful. We are not saying that reality holds an accessible replay of every moment in a way human consciousness could browse like a gallery. We are saying something subtler. That the universe may be extraordinarily reluctant to permit absolute erasure. That is a very different claim, and perhaps the most honest one science can offer. There is something almost sacred in that reluctance, even though physics itself would never use that word. The laws seem to resist oblivion. Again and again, when reality appears to destroy detail, we find instead that the detail has been transformed, distributed, hidden, encoded, or carried forward in ways we had not first noticed. Fire looks like destruction, yet it is transformation. Entropy looks like forgetting, yet it is dispersal. Black holes look like erasure, yet they may be horizons of encoding and eventual release. Even the emptiness of space turns out not to be truly empty. The universe keeps refusing to be as forgetful as it seems. And once that pattern reveals itself, it becomes hard not to wonder whether forgetfulness is more often a limit of observers than a property of reality. Maybe we forget because we are small. Maybe the universe does not. If that is true, then cosmic memory is not just about dramatic phenomena like black holes. It is also about ordinary existence. A planet orbiting a star is already a memory of how matter gathered long ago. A river is a memory of terrain and rain. A body is a memory of evolution and ancestry. A mind is a memory of genes, childhood, language, injury, care, repetition, and time. A civilization is a memory of countless other forgotten lives layered beneath the visible present. The whole world is inheritance. And inheritance is one of the purest forms of memory. This can change the emotional meaning of everyday life in a subtle way. It does not make us immortal in the usual sense. It does not promise that our personalities persist intact somewhere in the dark. It does not turn physics into theology. But it does suggest that our presence in the universe is not instantly disposable. The fact of our lives enters reality more deeply than human memory alone can measure. Your words alter nervous systems. Your choices alter trajectories. Your existence alters the distribution of matter, energy, and consequence around you. The world after you carries the fact that you were here. That is not grandiosity. It is continuity. And continuity may be the deepest kind of remembrance the physical world can offer. There is another reason this conclusion matters. The black hole paradox began as a threat. It seemed to open the possibility that the universe does, in at least some places, truly destroy information. If that had turned out to be correct in the strongest sense, the cosmos would be more fragile than it looks. The past could tear. The record could end. Distinct histories could collapse into the same future with nothing left to distinguish them. Reality would become less faithful to itself. That possibility is what gave the paradox such force. But the decades of work that followed have pushed many physicists toward the opposite intuition. The solution, whatever its final form, is increasingly expected to preserve information after all. Perhaps through subtle correlations in Hawking radiation. Perhaps through the horizon. Perhaps through holographic encoding. Perhaps through a deeper framework in which gravity and quantum theory are two surfaces of the same hidden structure. We do not yet know the final answer with full confidence. That uncertainty matters too. Science is still in the middle of the story. It has not reached the end. And maybe that unfinishedness is appropriate. After all, this question is not asking only how black holes work. It is asking what kind of universe we live in. A universe that forgets absolutely, or a universe that remembers through transformation. A universe where events can fall into perfect nothingness, or a universe where even darkness keeps the record in ways we are still learning to see. We are still discovering which of those is true. But already, the signs are suggestive. The surface of black holes matters. Entropy and area matter. Information and quantum evolution matter. Spacetime may carry permanent scars. Boundaries may encode interiors. The cosmos may be built from informational relationships more fundamental than our usual notions of objects in space. All of these hints lean in the same direction. Toward a universe that keeps more than appearances suggest. Toward a cosmos whose silence is not emptiness, but encoded history. Toward a reality that may be less like a passing stream and more like an accumulating record. This has a philosophical consequence too, though we should move carefully here. If the universe truly preserves what happens, then time itself begins to feel slightly different. Not unreal, and not frozen, but layered. The past does not continue as the present, yet neither does it become pure nothing. It survives in consequence. In altered structure. In boundary conditions. In fields, particles, geometry, radiation, inheritance. The present is not separate from the past. It is what the past becomes. And perhaps the future will say the same of us. There is a calm dignity in that thought. We are brief, yes. We are fragile, yes. We forget, yes. We lose almost everything at the level of personal memory, family record, and civilization. But maybe reality itself is less wasteful. Maybe every genuine event joins the deep conservation of the world. Maybe being here is enough to enter the archive. Maybe what is gone from sight is not gone from the fabric. Maybe the universe remembers not by holding still, but by carrying forward. That is a very different kind of immortality than humans usually imagine. It is not about selfhood persisting unchanged. It is not about a replayable copy of the person. It is not about preserving form forever. It is about irreversibility of occurrence. Once something real has happened, the universe is permanently different. It can never return to the exact state in which that thing had not happened. The event is now part of the causal body of the cosmos. It happened. And because it happened, everything after is altered. That may be the simplest expression of cosmic memory. The universe remembers because it cannot honestly become the same universe again after what has occurred. And if that is so, then the black hole question becomes even more profound. Because black holes were never only about black holes. They were the hardest possible test of whether the universe keeps that promise. If the promise holds even there, at the horizon of no return, then it may hold everywhere. If the record survives even through darkness, then perhaps forgetting is not built into reality nearly as deeply as we feared. That is why the story of information, black holes, and cosmic memory is so compelling. It begins as physics. But quietly, almost against its own will, it becomes something more reflective. It asks what it means for something to be real. It asks whether the world honors its own past. It asks whether disappearance is the same as erasure. It asks whether silence is empty. It asks whether what has happened can ever stop mattering in a universe governed by law. And perhaps, after all of that, the best answer is still the quietest one. The universe may remember. Not lovingly. Not narratively. Not in words. But in the patient language of structure. In the faint afterglow of ancient light. In the chemical memory of dead stars inside living blood. In the scars of spacetime. In the correlations of quantum fields. In the horizons of black holes. In the way the present refuses to arrive untouched by the past. The cosmos may not be a storyteller, but it may be an impeccable witness. That does not solve every mystery. It does not remove the ache of impermanence. Human life will still feel brief. Grief will still be grief. Forgetting will still happen in minds and cultures and records. Names will still fade. Photographs will still bleach. Languages will still disappear. Stars themselves will go dark one day. And still, beneath all that, reality may remain less forgetful than we are. Maybe that is enough. Enough to make the silence feel different. Enough to make the night sky feel more inhabited. Enough to make existence feel less like a vanishing act and more like an inscription. Enough to let the idea settle gently in the mind before sleep. That nothing real passes through the universe unnoticed by the universe itself. That every event enters. That every life alters. That the cosmos, in its vast and indifferent way, may carry everything forward. Not as memory like ours, but as memory deeper than ours. If you enjoyed this slow journey through one of the strangest questions in science, you can gently like the video, subscribe for more calm explorations of space, time, and reality, and leave a comment sharing your own feeling after all of this. Do you think the universe truly remembers, or do you think some things are still lost forever? And as you let the question drift with you into the dark, maybe one final thought is enough. The universe may not speak, but perhaps it never really forgets.